Okay, are we live? Great. All right, welcome everyone. I'm Lindsay Cooper. I'm this year's Haskell Symposium Program Chair. I want to thank all of you for being here, all of our speakers for their hard work preparing talks, and the ICFP organizing team for everything that they've done, including and especially the AV team. Can I get a round of applause for the AV team? And I also want to thank the Haskell Symposium Program Committee for all of their hard work, as well as the steering committee for their guidance. And I'll be saying a lot more about all that in my program chair's report tomorrow. But for now, I want to introduce our first keynote speaker, Ravi Chugh. Ravi completed his PhD at UC San Diego with Ranjit Jala, where he worked on information flow analysis for JavaScript and then dependent types for JavaScript. After joining the University of Chicago as a professor, he began working at the intersection of functional programming and human-computer interaction. He created the Sketch and Sketch system, which combines programmatic and direct manipulation user interfaces, and he's also contributed to the Hazel system for live functional programming with typed holes. The goal of Ravi's research explorations is to make programming more interactive and tangible, like GUIs, and to make GUIs more transparent and powerful, like programming. He also regularly teaches Haskell to undergraduates in his functional programming course, as well as courses on creative coding and user interfaces for programming. And I encourage you to take a look at his website, where you can find not only his impressive CV, but also his co-CV, where he lists all of his paper rejections. And today, he's going to be telling us about the next 700 block-based editors, including one for Haskell. Let's welcome Ravi Chugh.
Thanks, Lindsay. Thanks, Lindsay. Can you hear me? Okay, great. Thanks, Lindsay, for that really generous introduction, and thanks for reminding me that I used to work on dependent types and information flow. I totally forgot that period of my life. I'm really excited to be here at the Haskell Symposium today. Looking forward to all of the talks, and I'm also excited to tell you about some of the work that we've been doing in my group at Chicago the past couple of years. And the goal of this particular work is to make pictures that kind of look like this. So these are code snippets, obviously, with lots of strange colors and shapes and graphical elements. And so today I want to tell you about why we're trying to make pictures like this and how we're trying to incorporate these types of visualizations into programming environments. So there's a few different sources of motivation for this kind of work. The first is captured by this quote by Marcus and Backer, who describe how after decades of continuous revolutionary development of hardware and software, one aspect of computer technology has shown resilience to change, and that's the presentation of programs themselves. The typographic repertoire and appearance of programs often remains little changed from the manner in which teletypes first printed out programs. Now, this quote is from 1982, but I would argue that things are pretty much the same, 45 years later. Basically, when we open up, our text editor or our IDE, we see, fixed width monospace font. Now, fonts have gotten a lot better in the past 70 years, obviously. There's other decorations. But basically, what we're used to seeing is plain text with syntax highlighting. That's kind of what we expect. Okay, and so our first motivation here, our first goal here is, can we rethink this status quo? Can we expect more from the systems that we use? Can we think about syntax highlighting being just maybe one setting on a knob of options that we might want to choose from? What if we wanted to visualize other kind of semantic information about our programs? What if we wanted to turn the knob further and see blocks for all of the kind of syntactic elements in our program? Maybe we can visualize type information, and so on and so forth. And ultimately, also allowing users to kind of customize styles depending on use cases and usage scenarios. Okay, and so this first goal is to ask, can we get more granular visualizations and integrate them into a single editor? The second kind of source of motivation relates to block-based programming environments. So this is Scratch, which has been a really influential block-based editor over the past many decades. On the kind of left-hand side here, there's a palette of blocks which you can click and drag into your coding area, your scripting area, and these pieces snap together. And most of the kind of program construction is through drag and drop interactions. And then text edits are used just to kind of fill in constants or small expressions like variables, things like that. Now, Scratch and other block-based editors have been really influential in classroom settings with young learners in particular. But as described in this passage here, blocks editors are inferior environments for writing code kind of more generally in a more practical setting because they lack the full range of tools provided by text-based IDEs. And so we believe that blocks editors need to be embedded into full-featured text-based IDEs to really get the best of both types of interactions. Okay, and so today's text editors and block-based editors are just kind of designed differently from the ground up. They don't integrate well. They don't really support kind of smoothly integrating both modes of interactions in the same tools. And so that's our second goal here. Can we imagine a text-based IDE where we can type as much as we want, but also get maybe blocks and other visualizations drawn that we can click on and drag around in order to perform certain edits? Okay, so that's the second kind of source of motivation. Another kind of related source of motivation is captured by this passage from a recent paper at Chi 25, where in their work they explore interactions inspired by drawing software to help edit text. And in their setting, the text is natural language, prose, like in a word processor. And in their system, they make an analogy between visual and text editing, where direct manipulations can shorten text, expand text, reorder text. They have tools for adjusting the tense and grammar of text, layers for organizing text. And so another kind of source of motivation for us is to adopt those similar kind of analogies, but for the purposes of modifying program text. Can we build interactive direct manipulation interactions for modifying program text? Now, this idea of designing a direct manipulation editor for code is something that we explored in a previous project called Sketch and Sketch. In that work, a lot of the techniques were about direct manipulation of the output of a program as a way to kind of specify repairs and synthesize new pieces of code. And we also started to investigate direct manipulation on the code box itself. And that's really what this kind of this third goal is, to continue asking the question, can we have interactive direct manipulation editors for code? So we want to have things like that knob where we can change what visualization is currently being rendered. We want full-featured support for both text and block-based editing. And then we also want things like maybe layers for organizing different parts of our program text. And hopefully a rich toolbox of brushes, rulers, sliders for performing different operations to transform and shape the program text itself. Okay, and so another way I kind of like thinking about this is if you think about a creativity support tool like Illustrator, Photoshop, Google Slides, where you have lots of direct manipulation actions to shape the object that you're working on, can we have the same for program text, where our object of interest here is a syntax tree? Can that be one of the many ways in which we go about specifying and working on our programs? Okay, so these are the kind of three sources of motivation here, each of which is, they're related, but they're relatively independent goals, each with interesting, challenges, questions. We can, pick any one of these and work on them for, quite a while. So why talk about all three of these goals, in one talk? What ties these three goals together? So one thing that ties them together is a rectangle. I can draw a gray rectangle around them. That ties them together. Another shape that ties these three ideas together is what we've drawn in blue here, which we call a ragged block, or a rock for short. As you can see, a ragged block ties these ideas together more tightly than a rectangle. And what is the point here? The point is if we're aiming for better code visualizations, if we're aiming for better block-based code editors, if we're aiming for more interactive interfaces for code, we think that each of these goals could benefit from having more flexible ways to style and render ragged text. Because programs are heavily nested in structure, obviously, if we've got some small fragment or many small fragments that we want to highlight and visualize and decorate in some way, ragged blocks might provide a means to that goal. Okay, and so in a little more detail, a ragged block is a rectilinear polygon, which can be ragged on all of the sides. So in contrast to, like in a word processor where you can choose left-aligned text, left-justified text, where the text on the right side is all ragged, a ragged block can be ragged all over. Ragged blocks can contain text. That's kind of our primary use case here, but they can contain other things. They can contain pictures. They can contain other rocks. They can be nested inside one another. Really, the important property is the kind of, the raggedness of the borders themselves, which allow them to be packed together. And again, because program text is heavily nested, heavily structured, importantly, ragged blocks can be nested together really, really, really deeply while still being relatively compact. Okay, so that's the goal here. We want this primitive that allows us to pack ragged stretches of text together as kind of tightly as possible while displaying and decorating that structure. Okay, so as an extreme example, this is a small program. It's very small. You can't read that, obviously. It's a 25 or so line TypeScript program, JavaScript program. And let's imagine that we have a style sheet that doesn't add any styles. Okay, so there's no colors, there's no padding or border or anything. But let's say we wanted to display each subterm in that program with 4 pixels of padding, kind of space out every element from its surrounding ones. At a kind of high level, this is what the resulting layout would look like using rectangles. So rectangles are the kind of basic primitive that conventional 2D UI toolkits provide, like HTML and CSS. This is what this 25-line program looks like using rectangles everywhere, and we just use random colors just to get something on the screen. In contrast, if we were going to use ragged blocks to render the same program according to the same style sheet, the high-level kind of bird's eye picture looks like this crazy-looking topographical map-like thing or something. What I want to say about it here is that it's narrower, so it's about 30% narrower than the rectangular-based layout. It's basically the same height, it's like 5% shorter. And I'll talk about other metrics for kind of evaluating or measuring compactness later. Width and height is just one kind of coarse-grained metric. Also, I want to point out that I'm not arguing that we want programs to look like this by default all the time, but just as an extreme example, if we wanted to visualize all blocks in this program, ragged blocks allows us to do that with less space. Okay, and then again, because we probably don't want to have such ragged borders everywhere all the time, our layout algorithms also have support for kind of smoothing out some of the borders where possible. So once we've computed that tightly fitting layout, can we then kind of inflate some of those borders without having to change the positions of any of those fragments of text? We call that kind of variation smooth rocks, smoother ragged blocks. Okay, so that's an overview of what we're doing and why. Next, I want to show a demo of, a very preliminary demo of a code editor that we're starting to develop that incorporates ragged blocks for a number of interactions. And when I say me or we, I really mean my awesome PhD student, Sam Cohen, who's over there. Do you want to wave your hand or stand up or stand on your chair, yell Carpe Diem or something? Okay, so yeah, so again, this is a very preliminary prototype that incorporates a number of kind of milestones, ideas that we've kind of presented in a few settings, as well as some work in progress that Sam has been doing the past few weeks to get this demo working. So we're going to see 2 examples in this prototype editor called Juice. The first example is going to be a Haskell program that will take some input string, some file, and count the number of non-comment lines of code. So for example, if we have this input file here with 6 lines, 2 of them are comments, 6 minus 2 is 4, so this program should just print the number 4. The second program that we'll see is a JavaScript program that doesn't take any inputs and draws 10 little rectangle or 10 little lines to the screen that kind of looks like pieces of confetti on the canvas here. Okay, so let's take a look at the first of our 2 examples. So here is a configuration of this prototype editor called Juice, which is configured to support a very small subset of Haskell, just enough to support this demo here. And it's a text editor. We can type things like hello world. But in addition, we have that idea about being able to change what visualization, what style sheet is being applied to this program. So to start, I don't have any visualizations on. We've got basic syntax highlighting, of course. Blocks is a visualization that uses ragged blocks to visualize all elements in the parse tree. There's a simple kind of colorful version of this as well. And there's a couple of other visualizations that we'll see later in the demo. But to start, I want to show that, as we might hope, a text editor would allow us to, change the contents of the text buffer. We can, be very excited about our gathering here today and print a, more emphatic error message. And you'll notice that the ragged blocks that are visualizing the structure here are being recomputed and re-rendered as we are typing. Okay, so we're starting to kind of mix that block-based visualization with arbitrary text editing. Okay, and so while I do lots of text edits, maybe the block style sheet might not be my kind of first choice. Maybe I don't want to see that all the time. And so for now, at least, we are kind of using a different style sheet called the inspector style sheet as kind of our default choice while we're text editing. And so it looks just like unstyled text. So we can focus on that while we're typing, but then we can also hover over and start to see some of that additional block structure. If the editor and the compiler has information that they want to convey, that can get dropped into the status bar as we're hovering. And so we'll use this inspector style sheet as kind of our default while we're in like a text editing mode of use. And so now let's start to build that program to count the number of non-comment lines of code. And so I'll start by getting the string from standard output or standard input. And now our goal here is to, as we can kind of see, the type of this whole expression here is string arrow IO unit. So we want to take that input string and do all of the work of the program. Okay, so that's what this expression needs to do. And I want to build this up as a pipeline of different operations. So first I'm going to break up that input into a list of lines. Next, I want to filter out or keep the lines that do not start with the comment delimiter. Once we have just the non-comment lines of code, let's count them. And then finally, let's print that number to the screen, or print that number to a standard output. Okay, and so far I've kind of stacked up this pipeline of functions, one on top of another. Now I need to actually use function composition to actually compose them. And so at this point, this is my first time at which I think I'm done writing down the ideas in my head. Maybe we can see, does this work? Does this type check? Does this run? And apparently it doesn't type check. So down at the bottom, there's some error message about pink and blue and red terms. And it's also actually offering to visualize the error in some way. So let's try that. And so here it is adding kind of pink and red and blue colors that kind of correlate to that error message. That's interesting. It's maybe too early in the morning for me to understand what this type error message is saying, so I'm just going to kind of ignore it. And maybe I'll look for other clues. Maybe I'll hover around as I'm trying to figure out what the problem is here. And one thing that's kind of weird now that I kind of look at it is the filter expression that I thought was going to look for lines that did not start with is prefix is actually kind of separated into two chunks. Somehow the predicate not is prefix got separated from the filter function. And if I look at my entire pipeline, I also kind of see that not all the things that I thought were in my pipeline are actually in a single block. They're not in a pipeline. So maybe this is enough of a clue for me to make a leap of faith to guess that maybe operator precedence is the issue here. So maybe I'll try replacing infix application with parentheses, and turns out that fixed the type error. So that's good. But the editor is now kind of suggesting that there's still a remaining warning, a remaining issue to consider, and that's a linting error here. So in general, a linting tool will have lots of different patterns that it's looking for. Currently, this particular prototype has one pattern that the linter is looking for, and it's found that to be a problem. And it's saying that, hey, when you have a chain of operators, when you've got a point-free expression, all of the operators in that pipeline should be working left to right or right to left. Okay, what does that mean? Let's maybe invoke the style sheet that it's offered for this little lint error it found. And it's pointing out in purple that this operator bind, in some sense, is a left to right operator. It takes its argument and passes it to the, more or less passes it to the function on the right. Whereas function composition, we can think of it as, calling the function on the left and composing it with the function on the, composing the function on the right with the function on the left. And so the suggestion here is, maybe you should, maybe I should use operators that are all flowing data left to right or right to left. And that seems like a reasonable, suggestion from the linter. And so let's see if we can adhere to that. One way we could do this is by putting the get contents at the very bottom with reverse bind. And so now everything is orange. Everything flows right to left. There's no type error. That's promising. But I really prefer left to right in this case. And so let's see if we can rephrase our pipeline here to have everything move left to right. And so to do that, I need to reorder the elements of my pipeline here. And so I'll start by maybe just reordering them to be in the order I want. So lines first, then filter, then count, then print. And now I'll go in and finish the details of using the reverse composition operator to stitch them together. Okay, and at this point, apparently this type checks. That's a good sign as always. The linter is confirming that the top level operators in this pipeline here are all moving left to right. That's good, and if we ran this program, we should see that it produces the number 4 that we wanted. Okay, so that's the end of this first example. The second example we want to show is kind of recorded in this video here, which I'll play. This is a different configuration of Juice. This particular configuration supports JavaScript, and in particular, a library called p5.js, which provide lots of niceties for rendering graphics on a canvas and interactive animations, things like that. And so here, I'm not really saying exactly what we're doing, but what the workflow is, it's kind of like you would expect in Scratch. You've got a palette on the left where we can drag and drop pieces of syntax onto our program, and we're using text edits to fill in small holes. We're filling in constant literals, variables, small expressions with text edits, even though this editor Juice could support arbitrary text edits. Here we're kind of simulating a block-based editor-like workflow. And so far what we're doing is we're picking we're going to draw one piece of confetti to start. We picked a random position xy. We're going to take that point xy and pick like a random point along the circle around it. And so this looks like 20 degrees maybe, 10 kind of pixels away from the center. And we're going to do just a little bit of fiddling here to kind of get the endpoint of this first line, this first piece of confetti that we're going to draw to the screen here. Okay, and so you can see as we're typing, we are making syntax errors. We're necessarily making syntax errors, which are getting kind of temporarily indicated in red, and then we kind of get back to a well-formed state the visualization kind of returns. Okay, so at this point, we should have our first piece of confetti. We drew a thick line onto the screen at some random position. But remember, our goal was to draw 10 of these lines, and so now is our time to start refactoring. So let's start to refactor some of this single function into a helper function that's going to allow us to draw 10 pieces of confetti instead of 1. So the way that we'll do that is by clicking on one of these ragged blocks, which is going to trigger a context-sensitive menu of refactorings or other structure edits like you might see in a other refactoring tool. And here what I want to do is extract some of the definitions in setup into a helper function. Okay, so I want to extract the definitions for the position, angle, and drawing that one line into a helper function that is parameterized by positions x and y. And so this transformation now introduces a helper function, which we'll rename up here at the top. Confetto is the singular form of confetti. So we have our helper function now. And now that I think about it, maybe we need more arguments to this function besides just position. Remember, we wanted to have like different rotations and maybe different lengths possibly. So we can also go back and say, you know what, we actually want to lift out some of the constants to be parameters to this function. So we can select the angle, select that distance or radius parameter, and make those arguments to Confetto as well. The default names here aren't the best maybe, so let's rename this one to theta or t to indicate angle, and then the next argument we can rename to be radius. That's going to be the distance of this, the length of this piece of paper. Okay, so now we've got to actually go back and fill in the rest of our function call to confetti, and rather than picking 20 always, let's maybe now pick a random angle, kind of looking forward to drawing 10 random pieces in a second. And so at this kind of milestone, we've redrawn what we had before, but now with the use of a helper function, which will allow us to then call this helper function 10 times to draw 10 pieces of confetti. And so again, let's use a structured transformation or refactoring that's going to help us finish this edit. And so in this case, I'll use a transformation called extract loop that's going to allow us to select, in this case, let's select the statements for picking a random position, picking a random angle, and then drawing a piece of confetti accordingly. And it sets up kind of a skeleton for loop around those selected statements, which we can fill in to iterate 10 times. Okay, and so at this point, we should have our final canvas of 10 randomly placed and positioned pieces of confetti. Okay, so that's the end of the second example that we'll talk about. Let's head back to the slides to kind of recap some of the interactions that we have seen here. And so as you kind of saw, these are two different configurations of the system so far. But in principle, all these interactions are very much a part of kind of some singular system that we'll be developing in the future. So the first interaction that we saw is that Juice is a text editor. We can type, and as we are typing, ragged block visualizations are being recomputed and re-rendered as we type. Of course, as we are typing, we're making syntax errors constantly, and so the incremental parser that we use localizes errors according to whatever algorithms and heuristics that it uses. And so for those syntax errors, we render them with kind of a single red text box, let's say, and any remaining well-formed parts of the AST continue to be rendered with whatever visualizations are being applied. Now, there are other structure editors like Sandblocks and Tyler that have more sophisticated parsing approaches. So for example, those systems have techniques for keeping track of when you've made a syntax error, what subsequent edits could be made at that point, at the cursor, or elsewhere in the program that would then return things to a well-formed state. And so incorporating more sophisticated parsing techniques like that could further streamline the text editing in the context of structural visualization. So that'll be really fun to explore. Another characteristic that we saw is this idea of applying multiple visualizations to the same program. We might want to switch between different views of the program as we are working. In contrast to these particular visualizations that are on this slide, all of which are generic in some sense, they apply to any program in the language that's being supported. We've also kind of hinted at how type checkers, maybe trace debuggers, other tools might want to generate kind of program-specific style sheets. Based on some program analysis, a tool could dynamically generate a program-specific style sheet. So we kind of saw how with that error message, maybe the type checker chooses to use colors to kind of correlate different program terms that are going to be referred to in the error message. Maybe those colors could be surfaced as style attributes to be rendered to the user to kind of have program visualization corresponding to some more verbose, more complete type error information that they'll read in their console. I think another interesting possibility for style sheets is to expose them to users. One kind of sample example that I like to think about is, let's say I'm a teacher and I am designing some homework assignment where the goal is to write the zip function. and the starter code or the skeleton code that I provide might have a main definition with a couple of test cases. But really, the point for the student is not to worry about that too much. They shouldn't focus on that. They shouldn't even change it maybe. So maybe I distribute a style sheet with the starter code that, among other things, selects all equations that have the main identifier on the left-hand side and grays out those equations. It's also easy to imagine how the editor could maybe even be told to disable edits to those sections, just prevent the student from modifying that bit of code. Or if not, locking those regions, maybe have a different style sheet that if there are edits to that gray area, show a diff or a warning to kind of visualize that some piece of the code that really didn't need to be changed differs from what it was to start. So I think this idea of exposing style sheets to users so they can inspect and modify and define their own, I think hopefully there could be lots of interesting domain-specific things that we could all come up with. Another interaction that we saw is drag and drop syntax editing. And so this works kind of like I think you would expect in Scratch or something. But one really interesting thing in Juice, I think, is that the block palette on the left is actually just another text buffer. And like other text buffers, you can have rocks visualized in them. I think it's also easy to imagine making that palette editable so that users could add and remove things to the side pane. You could imagine having multiple side panes as Scratch spaces where we could move things back and forth from some temporary Scratch area onto our main programs. And so I think there's lots of cool things that remain to be done integrating this kind of drag and drop editing workflow into a text-based editor. And the last kind of interaction that we saw was how we can start to hover over and click and select ragged blocks as a way to trigger refactoring workflows with context-sensitive menus. This workflow is something that we explored a little bit in the Sketch and Sketch project in the Deuce editor. But there was kind of a single top-level ragged block, but now that we can draw nested ragged blocks that kind of can space out from other elements, it'll be interesting to see what kinds of more complicated, more complex, realistic transformations might be able to be surfaced through this type of user interface. Okay, so that's a demo of kind of the interactions that we're kind of currently exploring. I need a juice break, and maybe this might be a good time to see if there's any questions that people would like to ask while I catch my breath a little bit.
If people ask questions in the room, can you repeat it so people on the stream can hear it?
I can do that. Thanks, Paulette.
Very cool demo. So one question I have is one thing I can see is how this tool can help junior students who just started learning the programming language maybe to understand the programming language better. So have you actually tried that in junior programming language courses, and does that actually improve their understanding, etc.?
Thanks for your question. And is it Yao?
Yeah.
Thanks for your question. Yao's asking about how this seems like maybe it could help with students learning programming and computer science in the classroom. Have we done that? Have we asked any students? Have we studied students? The answer is no, not yet, but we definitely are planning to, and I'll talk later in the talk about some specific thoughts we have about that.
Okay,
so,
great, thank you.
Okay, I've had my juice break. Why don't we carry on? So next I want to talk a little bit about how some of the kind of techniques are working. How do we go from a two-dimensional layout system that supports rectangles everywhere to one that supports rocks? I want to give a flavor of some of the kind of concerns under the hood. So first, let's talk about how we might implement a code display using rectangles, using an existing toolkit like HTML and CSS. So there's two approaches that I want to describe. One approach for implementing a code display using HTML and CSS is what I'll call a flat display. So with this approach, the document, the data that's actually going to be rendered to the screen, the HTML document essentially has a two-level grid-like structure. There's a list of elements, which here I've called them divs, dividers. So there's going to be one divider, one element per row. And then each of those rows is going to be a list of elements, one for every character, or maybe every token, or every span of text that needs to be styled in some way. Okay, so the structure of this display is a grid of spans. Each of these spans could be selected to change things like font size, font color, background color, those kinds of decorations. But importantly, with this kind of approach, each individual element in this grid cannot be spaced out from other elements. If you tried to kind of move its position, it would just kind of hide something else. It doesn't push everything else around it. Okay, so that's an approach that I'll call a flat display. In contrast, another approach that we could take using HTML or another kind of box-based layout model is what I'll call a nested display. And again, this is very small text, don't read it, but the point is to show that the structure of the document in this case is more nested. It's in one-to-one correspondence basically with the input AST. So every time you have a subterm in your input data, you have a corresponding span in your display, which could be subject to whatever styles you want to apply. And so in this approach, with a nested document like this, each span could be displayed as a rectangle called an inline block in CSS. And importantly, with inline blocks, with rectangles, you can set padding and border and margin to kind of space those elements out. And you get this nested looking display that we see at the top. Okay, so these are kind of like two approaches to implementing code displays using rectangles. Now, we've been talking this entire time about wanting to have nested displays. We want to be able to visualize program structure if we want to or need to, but we would like to do that more compactly than when using only rectangles. So our first goal is to generate more compact nested displays. But once we've done that, assuming that we can compute some positions and ragged block polygon outlines, all that kind of stuff, the question is how do we actually render that to the screen? How do we implement it? And our second goal here is to try to reuse or try to encode these ragged block layouts in an existing grid-like structure as much as possible. Because there's lots of tools like text editors and IDEs and other text visualization tools that are already implemented in the world. Many of them have this kind of grid-like structure to them. So if we could encode our ragged block layouts in terms of a flat structure, that'll allow us to try to extend existing tools as much as possible rather than building up everything from scratch. Well, not scratch, from the beginning, I guess. Okay, so I've been talking about compactness a lot, so let's talk a little bit more about that at a high level. So rectangles are kind of the default in a system like HTML. Before ragged blocks, we've also explored an intermediate kind of point in this space, which we call S blocks. So an S block is a rectangle where the top left corner could be missing. It doesn't have to be, but it could be missing. And then the bottom right corner could be missing. And so this shape kind of looks like what you often see in an editor with text where you've selected some multi-line text that often has this kind of shape to it. And so this shape does allow us to pack text a little bit more tightly than with rectangles. But then going further, using ragged blocks, we can even more tightly pack nested text together. Okay, and so I'm not going to talk about exactly how we evaluate compactness on benchmarks, but one thing I do want to mention is earlier I talked about how the overall width of a display might be narrower and might be shorter. That's a really coarse-grained metric because what if you have one really long line? The width of the overall layout only captures that longest line, but there's lots of other lines that we're reading and writing and might want to have some information about. And so a much more granular notion of compactness that we've considered is something that relates to the entire grid itself. So if we think about the grid of text elements in our program, each of them has a position when we don't apply any styles. And so if we think about the positions of all of those elements, when we render that same program using structured visualizations with whatever blocks and other decorations are being applied, that grid, that mesh is going to stretch a little bit. Some of the elements are going to get pushed to the right, and some elements are going to get pushed down. Those differences are kind of indicated in red here. That distance, those quantities are what we really want to measure if we're talking about how much did a layout change with respect to the kind of unstyled flat text. And so in our kind of work, we evaluate this notion of how much did this mesh stretch when evaluating different layout algorithms. And I'm not going to, again, talk about the benchmarks in detail, but from a high level, when using rectangles to lay out various benchmark programs, that's going to kind of represent the approach that has the most horizontal and the most vertical error when compared to an unstyled layout. That middle ground that I mentioned briefly called S-blocks, using the algorithm that we have so far explored to compute S-block layouts, that tends to reduce the amount of horizontal error for lots of the fragments in our benchmarks, but the vertical error actually ends up being pretty similar, sometimes even a little bit larger in order to kind of make room for squeezing stuff horizontally. But then again, in our benchmarks, ragged blocks allow us to reduce both horizontal error as well as vertical error compared to the kind of conventional approach, which is using rectangles. Okay, so that's just a flavor of how we are thinking about evaluating and measuring compactness. Next, I want to give you a small kind of like flavor of how some of the layout algorithms are working under the hood. And so we'll do that in terms of this, this JavaScript TypeScript program that computes the absolute value of a number. So this program is represented by a syntax tree, a concrete syntax tree. Here, this concrete syntax tree has all of the tokens and all of the white space stored, so we can construct the entire display verbatim. And let's say that from somewhere or someone has chosen these particular styles to apply. Let's say we want to visualize rocks everywhere with 2 pixels of padding, and we've chosen 4 of these sub-expressions to have different colors. There's a red one, there's an orange one, green, and purple. How do we go from this syntax tree with this style sheet to some picture at the end of the day? And so this will be kind of a series of steps that process this syntax tree, starting by considering each fragment kind of as some like atomic piece of data that's eventually going to get wrapped and combined with other graphical elements. So one of the key operations inside the algorithm is called wrap, which takes a fragment to start, but eventually it'll take an arbitrary ragged block and wrap it with like more layers of padding and border and margin. So let's just look at like this arrow delimiter or this arrow token in our syntax tree. The arrow is under like one level of colored ancestor here. It's got a red parent. And so if we look at our picture here, we see that the X or the arrow token is within a red region, a red polygon. If we looked at like -X, for example, here those tokens are, they descend from green and orange and red. And so if we look at the corresponding display for -X, those are surrounded by green and orange and red. And so wrap conceptually is going to take some ragged block that has been processed before and adds additional layers of polygons and wrapping to it. Another operation is going to say, okay, you've got a couple of adjacent ragged blocks. Now we want to join them because they are adjacent on some line in the original program. So I'll go back for a second. If we look at the second line in this output, the x less than 0 question mark -X, if we call join h, that's going to smush them together. And importantly, it's going to determine what layers of like shared wrappers do adjacent elements have in common. So all 3 of those rocks had orange and red in common, and so those can be fused without keeping kind of separate, isolated orange-red regions. Those have been fused, while the purple and green sections were not shared among siblings, and those remain islands from each other. Okay, so there's ways of kind of unwrapping and fusing together similarly layered rocks. And then after doing lots of wraps and join H's, eventually we've got a bunch of lines that have been processed, and now we want to vertically smush things together as well. So join V has a similar kind of notion of fusing similarly wrapped rocks as much as possible. Okay, so that's kind of a small flavor of some of the helper operations that go into these layout algorithms. And there's lots of kind of details that if you're curious, please take a look at the paper and other kind of software artifacts that have been released. But a couple of the kind of like key intuitions are that one of the details that's important to get right is the representation of new lines. So a new line, creates a new line in the linear buffer, but they create two sections of the same node in our data to begin with. So we need to be careful to not kind of break up that single node into two separate pieces. Unlike other concrete syntax in our tree, new lines need to be kind of treated specially because they have this effect of creating separate lines while still referring to the same node itself. Also, I kind of hinted at the fact that there's lots of operations for wrapping and then unwrapping and rewrapping. And so there's data structures and optimizations to kind of help make it easy to do lots of set operations on rectangles often. And so again, please see the papers for more details about that, as well as other kind of variations on the layout algorithms. So sometimes we might want to align certain characters in our input buffer. Sometimes we might want to smoothen out those rock borders. And so there's lots of other kind of like low-level details and choices to make in layout. And again, we've evaluated these algorithms compared to kind of conventional rectangular-based algorithms, as well as other approaches. Okay, so that's a little bit of a flavor of how we compute ragged block layouts. Remember that another goal is to try to encode or represent or implement those layouts using a flat grid-like HTML display if possible. And to do that, we start with a flat display. So this HTML document that's kind of really small on the left is a list of rows. Each of those rows is a list of columns. We start by systematically inserting a bunch of placeholder elements, a bunch of spacer elements that don't have any content, but based on the positions and other attributes that have been computed in our rock layouts, we can set the width and height of all of those spacers to kind of stretch the mesh and have all of those text fragments kind of move to where we want them. And then we can use SVG shapes to draw all of the polygons. We can set all the colors and polygonal borders that we need to display the final visualization. Okay, and so we are able to encode a lot of these new visualizations using kind of an existing architecture for how code editors are often implemented today. Okay, so I've talked a little bit about an idea of how some of the concepts work under the hood. Back to Yao's question about how might we use these ideas in a classroom, that's the next kind of question and goal. Because block-based editors have been used a lot in settings, especially with young learners. Scratch has been used with elementary school students, middle school students, high school students. There's also a version of Scratch called Scratch Junior, which is particularly designed for the youngest of these learners, kindergartners, first graders, second graders. Scratch Junior has like has a smaller selection of primitives. It's got fewer events that you can deal with. It's got a simpler kind of interaction model. So you might start with Scratch Junior when you're really young. You might have a curriculum based on Scratch when you get older. After that, there's another block-based editor which is really interesting called Snap, which has a different programming language inside of the system than Scratch. Essentially, it's like Lisp. It's got higher order functions and metaprogramming and reflection. It's essentially a Lisp under the hood, but with a block-based editor. It's got Scratch-like motifs and builds on all of that. And one interesting thing is that there's a curriculum at Berkeley called the Beauty and Joy in Computing, which is designed as like an AP CS curriculum or maybe a kind of intro CS course for early college students. And in that course, they start by using Scratch to teach intro CS and programming. And after a while, they end up switching to a different language, Python, with kind of conventional text-based tools. So if we kind of look at this landscape, there is kind of a path through block-based editors to text-based editors. You can use block-based editors to kind of learn more and more advanced concepts, and eventually you kind of graduate to Python, I guess. But there's lots of aspects about this kind of landscape that I think beg further questions. For example, students, as they're learning to program in a block-based language, sometimes kind of question the authenticity of the tools. Are they really learning the kind of concepts and tools that will be useful to them as they do more advanced work in the future? Furthermore, blocks and text, I think, intuitively, they're just different interactions. Some people might prefer one versus the other. In some usage scenarios, one interaction mode might work better than the other. And so it's natural that there is this question of trying to bridge both blocks and text-based editors. And so now that we are starting to be able to do that with ragged blocks, the kind of pie-in-the-sky goal is, can we now start to infuse text-based editors for not just the language inside Scratch or the language inside Snap, but any language that we might want to use in a classroom setting? Can we enrich that with ragged blocks and block-based interactions and smoothly mix both blocks and text into classroom settings? And so we're planning on doing this in a couple of specific courses that we teach. So one is a creative coding course that we teach, which is kind of targeting a broad variety of student backgrounds and student interests. Students that probably otherwise wouldn't take like a formal CS course with us and are unlikely to kind of major in CS. And so we use lots of kind of interactive and graphical digital design types of projects and examples to to couch all the CS kind of foundations that we're teaching. And in previous work, we instrumented the P5.js editor that we use to study how students use the editor. How often do they use different features in the system? We also kind of survey their experience with different tools and have started to kind of integrate some modest novel features in the editor. And so we're planning on developing more of these style sheets for conveying information about lint errors and runtime errors and things like that into the editor, as well as, again, trying to augment the editor with some support for block-based interactions as well. And so we plan to be doing this in the coming years. We've been talking so far about kind of introductory level programming, and that's where block editors have almost entirely been studied so far. But again, part of the goal here is to not limit block-based editors just to classroom settings and while you're learning, but if they are integrated with text-based editors, why not? Shouldn't we also be able to use them for benefit beyond introductory settings? And so another specific course that we're interested in kind of experimenting with these ideas is a functional programming class that we teach in Haskell, which of course kind of colors the types of ideas that we are teaching. But importantly, it's a kind of upper level class where students have been programming for some number of months or years or more and are very comfortable with programming. Can we use these types of interactions to hopefully provide benefits even to students that are much more advanced than in our earlier courses? Now, one silly little thing that I have enjoyed that we've done in kind of previous iterations of this class is one of our kind of course materials web pages has this silly looking syntax guide, so that every time we see new kind of expression or a new kind of type or a new kind of kind or something, we kind of add it to our grammar of syntax that we have learned and kind of color code it to maybe try to make it maybe easier to help remember, oh, this is where like expressions can go. This is where types can be written. This is where values kind of pop out. And when we learn some new feature, and there's lots of syntactic features in Haskell that kind of come out, maybe we can relate them to things that we've seen before, again using these kinds of like block-like color coding schemes. These are all like really hand-coded, terrible CSS that just work for small rectangles. Now that we can do this more systematically, again, can we develop interesting code style sheets for conveying different information in our course materials and in our editor? Can we get block-based interactions in our editor? Is it useful for more advanced students to use those kind of features? These are questions that we haven't studied yet, Yao, but we definitely plan to and would like to. Okay, so I've said how we haven't, talked with users yet. We haven't studied users yet, and so maybe it's worth asking: is this even a good idea? Should we try to, do this? We haven't, done like formative studies with, kind of students in a small setting yet, but there is some anecdata, I guess, that I find promising at least. So about this time last year, I happened to run into an 8-year-old. He was in 3rd grade. I won't tell you their name for privacy reasons. But this, anonymous third grader happened to see me making a slide with a picture like this on it. So again, I can't tell you who this is for privacy reasons. But they saw this picture, and the first thing that comes to their mind is, hey, that looks like Scratch Junior. So apparently this third grader had been using Scratch Junior in their class to make silly, fun, interactive pictures and birthday cards for their friends. This apparently looks like Scratch for JavaScript or Scratch for Haskell. That was pretty promising. That's kind of what we're going for here. Can we have Scratch for Haskell? They followed this up by saying that everything inside this picture doesn't make any sense. It definitely needs more work. And fair enough, I agree. This needs more work. So that was one encouraging anecdote. Now, a few months later, I happened to bump into this same third grader. They were still 8 years old, still in third grade, still anonymous. I can't tell you, their names for privacy reasons. And this young fellow shows me their homework. They asked me to check their homework. And apparently their homework assignment that day had been to compute the perimeter of rocks, apparently. This was their worksheet. That was also pretty promising. So apparently ragged blocks are already in a third grade classroom. Maybe that gives hope that we can bring them to fourth grade and fifth grade and 16th grade and beyond. So anyway, so no user studies, no humans yet besides this very informal anecdote. Okay, that's enough fun. Let's get back to serious work. And the serious work left is just to kind of wrap up with where we would like to see this go next. So again, really the goal that I've been describing here from the beginning is, can we get blocks into editors for every language? How many languages are there? Apparently, as of a few weeks ago, there are officially 751 programming languages. I don't think this number reflects all of the cool languages that have been proposed and presented at ICFP and Haskell this week. There's a little bit of a lag, but let's not worry about that. Some of these languages already have block editors, so Scratch and Snap are on the list. We are working hard on Haskell and JavaScript and related languages, so more or less there's 700 languages left in the world that need block editors. So if you would like to help us with that, we would appreciate it because we're not going to get to all of them. If we had more clients for the the ideas and the tools that we're building, and again, that Sam has been working hard to build, it would be great to have more kind of applications to kind of stress test these ideas. After we accomplish this goal, after every one of these 700 languages has a block-based editor, another natural question is, what about other types of languages, like natural languages? Those have lots of structured elements as well. And if we're used to using tools like Microsoft Word or Google Docs or something, we're very familiar with the red squiggly line, which is the conventional way of conveying spelling error. We're maybe familiar with the blue squiggly line for conveying grammar errors. It's hard to convey all information about some passage of prose using just squigglies. What if there's lots of things that you want to be conveyed? It's hard to nest squigglies together. And so it's natural that we want other kinds of decorations, other ways of decorating maybe natural language text for conveying information. And so there's been lots of interesting research prototypes that have proposed different ways to visualize and control multiple selections, find and replace across large passages of text. This figure at the bottom right here, TextoShop, is the tool that I referred to early on in the talk, where they've added sliders for kind of changing the tense and grammar, or I guess the kind of like the verbosity and concision of text. They've added color pickers for the tense and grammar of text. So there's lots of precedent for exploring different mechanisms for conveying information about natural language. And so the idea is, could we use ragged blocks as another tool for conveying information about prose? So this is just kind of a hello world example of maybe in some future, maybe there's ways to convey multiple errors at once. If you've got a grammar error that contains a spelling error, that contains a suggestion for rewriting one word to another, maybe all of those could get smushed together in some useful way using ragged blocks. Maybe differences between different versions could be visualized in some ways. So these particular pictures themselves are not, the end-all be-all, certainly, but the question is, can we figure out whether, ragged blocks might be one more tool to help convey information about text in interfaces that render prose and other types of text. So here is a mock-up that we kind of enjoy. The top right little screenshot here is taken from a math Stack Exchange post where the user was asking a question about some formula. So they used like a free-form drawing tool to annotate some of the formula, and they asked a question about it. Others commented and kind of had a conversation about this. In the future, maybe a ROCs-enabled tool of that sort could allow directly structurally selecting different elements that could be connected to and visualized in the conversation, and when the user makes changes to the selections, all those things are kind of correlated. So again, the idea is, can we use ragged blocks as yet one more user interface primitive in a variety of tools that are rendering structured text and data in different formats? Speaking of user interfaces for text, the elephant in this big room, my colleagues and students tell me about these tools that are out there these days that apparently take your command and generate lots of text. I have no firsthand experience with these tools, but I'm told that they're generating lots of things, lots of text to read. And so the natural question is, again, in some future, probably there'll need to be interfaces that, convey more information about the text that's being generated and why. How does this relate to the, the request? What are some alternatives for, this, piece of the output? What is the history? What is the provenance of different pieces of the generated text? And so again, among other options, can ragged blocks be yet one more primitive that could be used to visualize information in a setting where there's lots of text to read and write and maintain? Okay, so that's all that I wanted to say. So again, our motivation here is really to try to build more primitives for better code visualizations that we can kind of hopefully switch between at different points in a programming workflow, enable better and more integrated block-based editors inside text-based editors, and more generally enable more interactive graphical direct manipulation editors for code and other types of structured text. And we hope that we can incorporate these types of interactions into a wide variety of programming language, but also natural language interfaces in the future. So if you'd like to learn more, we've got a few papers with kind of corresponding software artifacts, videos, things like that. So please take a look and get in touch. Thanks to the ICFP organizers and the organizers of the Haskell Symposium, and thanks to all of you for listening. So I think we've got plenty of time for questions.
Thanks for a great talk. In the editors that I use, I'm quite addicted to autocomplete, but I only am presented with one choice at a time, and usually there's many possible choices with a common prefix. So is there something that blocks could help with here to let me better grok all my autocomplete?
Absolutely. And should I still repeat the questions? Excuse me? Should I repeat the questions? No need. Okay, great. Thanks for your question, Satnam. Yeah, so in terms of autocomplete, could these ideas, these techniques help to understand maybe not just one possible completion, but a menu of completions? I think the answer is certainly yes. We haven't done anything specific with that, but there are some editors that I think have started to come up with nice, like, context-sensitive menus to offer choices. So in the Hazel project and the Fructure structure editor before that, again, like, you get a menu of options, and maybe those could be color-coded in some ways. Like maybe if you know for some reason that, I don't know, some operators, take data left to right or right to left, maybe those colors could be surfaced in the context-sensitive menu that is being suggested. I think there should be lots of fun possibilities like that. We haven't done anything specific, but I think certainly that's a great avenue to explore. How can we try to provide more information as users are making choices about what to write next or what to choose from a menu of options next?
Thank you.
Great talk. As a working programmer now, I spend probably the majority of my time, and this was even before the age of AI, reviewing code, that is, looking at changes to code made by other people. Have you folks thought about something like a blocks editor or a blocks visualizer in that setting where we're trying to look at how code has changed or evolved over time?
Yeah, that's a great question. Reading code, reading revisions of code, version history is something that I feel like there must be, good ways to visualize, structural changes and semantic changes to programs beyond our, common line-by-line based red and green diffs, which are great for lots of reasons, but not for every purpose. And so we haven't done much specifically yet, except that towards the end of the talk, I flashed a couple of very hello world example visualizations for kind of showing differences in natural language text. We've also got a very, very simple example that visualizes a change to a program structurally. You can imagine using nested blocks to kind of show how the nesting structure has changed here. You've introduced some additional level of scoping, which is kind of not just indented all of my lines on this stretch, but has actually introduced new bindings and the types of those bindings. So we haven't specifically thought of kind of good visualizations for structural or semantic diffs, but it's something that I think would be great for exploration. And if you have thoughts, we would love to hear it.
Great talk. One thing I noticed is in the beginning you had an example where you had to sort of drag and drop, and then later you had sort of the measurement on how good the ragged blocks was, where one of the notions of a better surrounding was that you were moving the text less. However, sometimes that causes sort of lots of lines to be drawn really close together, and you can even see that a little bit with the drag and drop. It's really difficult to actually get the drag and drop at the right position. So I wanted to know if you've explored either other metrics of how good it is to surround things with blocks, or maybe even something where you use type information or something like that to sort of artificially widen or shrink different drop targets.
Yeah, that's a great question, Sky. So in terms of figuring out what the right sizes are for these different interactions, we haven't specifically done that, but there is a bunch of relevant and related work in the HCI literature on exactly this topic. Like one long-running project that I'm familiar with, among others, is called Bubble Cursor. There's lots of different ways in which folks have tried to figure out how to make drag and drop and other kinds of direct manipulation interactions the most usable. And so I think, as you suggested, there might be some times in which maybe, even if, let's just say statically I was happy with the amount of padding, while I'm doing some interaction, maybe some heuristics, maybe some prior experience would override those choices and dynamically add more space, maybe even based on types like you kind of suggested. I think those are all great possibilities. We haven't done anything specific, but it's a good reminder about this literature on, really classic literature on drag and drop cursor interactions. We'll take a look.
Okay, thank you.
So one of the things I really like about this is the way it's inspired by powerful professional tools from very different disciplines, like Photoshop or Premiere, which is always a fun thing as a programmer who spends all of their time in text-based tools to see what somebody who's really good at Photoshop is like when they're working on it and how productive and powerful they are. I wonder, but I'm sure you've had the experience of meeting people who are programmers who have Vim configured such that they are moving at a speed that you did not realize was possible through some code base or making some changes. And I wonder if there's interesting inspiration for user interfaces that can be taken from what people like that are doing with programming into actual editors and surfacing those features as real features of the system rather than as things you can write in Vim script or Emacs Lisp.
Yeah, you touched on a lot of interesting comments there, Sam. I guess what I'll kind of touch on is a lot of the motivation that I described was kind of taking drawing software GUIs and trying to figure out analogies and how to integrate them with code. You're asking maybe what if we go the other end and get the super power users that have really interesting purely text-based workflows, how do we kind of somehow provide graphical features that might help with those workflows? That's a great idea. I don't have a specific answer except that one user study actually comes to mind. Justin Lubin several years ago studied how Haskell programmers, other typed functional programmers was the name of the paper, how they go about, working on larger, projects of their own, how they go about debugging type errors, how they plan different changes. And, I think that paper had like a classification of different types of edits. I think studies like that could be a really good source of inspiration for, is there something about that even while retaining an existing power user text-based workflow, maybe there still is some opportunity for a visualization to help with that, even if it's still keyboard-driven. I think that's a great idea. And you also mentioned how, as a kind of, I think multiple people mentioned as like working programmers, practical programmers, reading lots of diffs, doing lots of, work on programming. I don't do any real-world programming these days, so if you know where to meet people that are interested in, helping us understand what, would be required to take these into more practical settings, please let me know.
Sure. Thank you for the awesome talk. I was thinking about how you showed a list of 750 some programming languages and how you have already checked some off the list. And so now we only need to get the other 700 and then we'll be done, right? So as Haskellers, we love embedded DSLs, often monadic DSLs. And it's really nice to be able to think in terms of that DSL. And sometimes we kind of accidentally create one, not even on purpose. And Haskellers aren't the only ones who do this, of course, right? The Racket language-oriented programming philosophy famously is all about this. So it's not really just 700 languages that we need block-based editors for, but it's an infinite number of languages. And I wonder if you have any thoughts on how to provide tool support for people who are creating DSLs like that, even like whether intentionally or unintentionally.
So there's good news. That 751 number was a joke. Yeah.
I did think you were probably being facetious.
Yeah, so yes, I mean, the good news is, just like, there's lots of other interfaces for plugging in a new language to a new system. Like, think about LSP or some other kind of interface that says you've got some new language or really any data type, and you want to connect it to some editor service. Here is the API that you need to, plug into, and then you get a whole bunch of the infrastructure, that comes with that. That's the same situation here. So, we've talked mostly about program text, ASTs, in this talk. It turns out there's, you can think of it as a type class interface that any data type could be added to that would connect, the structure of that, values of that data to different visualizations that you want to convey. And from there, that internal representation is kind of, manipulated opaquely by the layout algorithms and all of that. So, we haven't figured out how to abstract some of the details to work over many different languages and data types yet, but I think certainly there is, and there are interfaces that will allow, your newest favorite DSL, you satisfy this interface, how exactly do you want to color or convey or style different elements of new language, and then, you're running.
So do you imagine, just to follow up on that, do you imagine a future where when somebody's publishing their new shallowly embedded DSL as a library on Hackage, that they also publish the style sheet that goes with that?
I never imagined that until you said it, but yes, that sounds great.
Thanks for the great talk. I thought that the maturity of block-based technique, the block-based technique is now matured, and now is the time to think about how to deploy that to 700 languages. And I wonder if there is any kind of language server protocol that can provide such service so that if, well, personally I want the one for OCaml, but if I want to make it, then how would it be possible to do that kind of things more easily for any languages?
Yeah, so how do we kind of really figure out nice abstractions for how to integrate and plug in and deploy and customize ragged blocks for other settings. We're not quite there yet. We're still figuring out like details. Like for example, even when coming up with new examples, we realize, oh, there's one more little choice in how the lines get, rendered. That should be another flag into the layout algorithms. There's also no support for kind of customizing the borders, in which case, in some settings, you might want to actually allow like customizations of the borders themselves. So there's lots of like other like little flags, options, details that would need to go into a nice LSP-like interface. We're not quite there yet, but I think the more concrete applications we have, the more we'll be able to figure out what is that right boundary so that a wide variety, 700 or more test cases could fit in rather than just the 2 or 3 that we have. So we're not quite there yet, but I think in the long term, yeah, our vision is that there will be these LSP-like interfaces that should be extensible.
Hello, thank you for the talk. So your system still uses text as the underlying representation of the program. In contrast to something like Scratch or Sketch or Snap, where it's actually just the AST underneath, right? So along those lines, I noticed you said you were using Tree Sitter for doing the incremental parsing. If like people make a grammar error, then it can still show the rocks for the rest of the program without issue. So do you imagine that this is kind of like a layer on top of existing tools for text editors? Like an LSP, for example, maybe there's like a default version of your editor that is derived from an LSP, and then you can add extra features on top of that. Is that your goal, or are there aspects of your approach that conflict with other tools for text editing?
Well, I think on this kind of like general question about like, is the primary ground truth representation text, or is it some other more structured information, AST, dependency graph? I think a lot of the techniques that we're developing apply to both, right? So there's in both a text-based editor as well as kind of like a more full-on kind of structure editor. There's still going to be pictures that need to be drawn to the screen, and the idea is that ragged blocks is one more type of element that could be useful in all of these settings. And so in terms of like the core layout techniques, we think they can be used for implementing editors that occupy all the different points on this kind of spectrum. In particular, in terms of the code editors that we're most interested in building, like this prototype that I demoed, we have always been on the kind of like text-first side of the spectrum, thinking that by augmenting text with more features, that's great, but you still retain the ability to copy paste into an email, or check into version control and get a line-based diff, or maybe a semantic diff as well. But you still have the flexibility of text-based tools. And so 2 answers, I guess. The layout primitives are generic. They can be used in any editors, however they're designed, in terms of their principles. In terms of our particular tools, we're probably going to keep developing editors that are text-based first.
Thank you.
Hi. Thanks for the talk. I'm so glad I made it here today. Yesterday, I was in Bloomington, hour south of here, teaching some students about Racket and introducing them to things like pattern matching, where I would have really appreciated rock-based visualizations while introducing these students to these Racket constructs. But so I was thinking about Racket in the context, or any kind of parenthesis-based language in context of your talk, and it feels like parentheses, this sort of pervasive grouping that's already visible in the source code, right, kind of compresses the spectrum that you're talking about, right? Because it feels like what rocks do a lot is to give you a little bit of room so that I could mouse over any sub-expression and select it and manipulate it, right? So, but in Racket or in Scheme, already I could just choose the parentheses, right? That already allows me to choose any sub-expression to operate on. So I guess on one hand, I was wondering how, like whether it may be already more, I don't know, the distance between some of the tools, the manipulation commands that you were showing, and Racket is shorter than for other languages, because I already kind of want to, for example, multi-select S expressions in my Dr. Racket, and then maybe do refactoring based on those multi-selections. But on the other hand, I was also thinking, okay, I really want this for Dr. Racket, and I don't want to touch the Dr. Racket GUI code, right? So in terms of deployment, instead of the next 700 languages, like is it possible to just not even go through a browser extension, but just like do like a compositing filter, right? Put on magnifying glasses, right? So have a way to interact with some existing editor where just by manipulating the actual pixels and stretching out that room between adjacent sub-expressions, I'm able to use existing tools and sort of retrofit rocks and manipulation onto existing editors.
Interesting. So two themes there. One, I like this observation that a fully parenthesized program already has all of the structural elements surfaced, right? And maybe one way to think about that is parentheses are a style sheet. You can think of it that way. Because there's some places where parentheses are not necessary and some syntax, obviously. You could think about parentheses as being a style sheet that doesn't also draw space out stuff vertically, it spaces out stuff horizontally with parens. That's a nice observation. In terms of your second thought, could we analyze raster graphics and infer retrofit rocks? I have no idea. Maybe. I mean, that'd be pretty cool. But I guess, so it depends on how much domain-specific reasoning you want to do, I guess. But like taking an arbitrary picture and then trying to figure out, what elements you want to wrap in blocks or not, I don't know. That sounds like a very general computer vision thing. But if you want to take something in a known language, you want to take, I know this piece of code or this screenshot is, Racket code, and analyze it and infer. I mean, once you have the parse tree, once you have the structure of the data, that's what you need, right? Like once you have the data in a structured form, that's what enables all of these choices about styling. So yeah, maybe you could retrofit some of these techniques in a setting without implementing them under the hood and kind of circumventing it by getting, OCR to give you an AST and then compute your rocks. I've never thought of that. Sounds possible. We're probably not going to do it, but if you wanted to, that would be a very fun direction to go.
All right, thank you everybody for all of the great questions. And it's time for the coffee break. So see you back here at 11 o'clock, and let's thank Ravi one more time for the great talk.
Thank you.
it in.
All right, everyone. So now we start our next session at Haskell Symposium. So first we will have Leo talking to us about evaluating shrinking.
Okay, let's see if that works again. That's not what you should be looking at. Much better. Although that one is the actual desktop background I have, so, I'm in the right place. Okay, so this talk is about evaluating shrinking, as Yao said, and this is joint work led by my recently graduated grad student, Alp, who could not be here due to travel and visa constraints, and also a master student, George. Now, this talk, as many, many talks throughout this conference, is about property-based testing. You've seen that a lot. In fact, a lot of the early slides for this talk are similar to something you might have seen earlier in the week, but I do want to just give a high-level overview of property-based testing just to make sure we're all on the same page. The example I'm going to use is an example I've also used in many different talks throughout the years, which is semantic preservation for optimizations, right? So we have a property, which is a predicate, an executable function from expressions here to booleans, and all this is saying is that if you evaluate an expression with and without optimizations, you get back the same result, right? Standard semantic preservation, very simple. We can use this to sort of visualize what happens when we do property-based testing. And what happens when we do property-based testing is we have to add some kind of annotations. Usually those are done using type classes, but some people are opinionated against that. And in general, you can have those be by users. You can have them be automatically provided. In the end, what you end up is you have a checker. And your checker is your property, and you have your generator, which produces random inputs. And in this case, it will produce random expressions. We're going to run those expressions. We're going to do that in a typed loop. And we're going to try that again and again until at some point we find some expression which yields a bug, right? So we are in a very happy situation. We found our bug. Now, the main topic of this talk is that whenever you find one of these bugs, it usually has a lot of noise, right? It has a ton of random noise because you've generated it randomly, and a lot of parts of that input are useless to debugging. So one of the ways we do that, we fix that issue, is with shrinking. We take those inputs, we pass them through what is called a shrinker, a function that produces smaller inputs for some value of smaller, and then we do a similar loop. We try that again and again and again until hopefully we find some minimal or locally minimal counterexample. And then we report to the user. That's property-based testing in the style of quick check in a nutshell, right? So we have a bunch of different components, checkers, generators, shrinkers, printers, runners. And while most talks about property-based testing will focus on the generator, I'm going to focus on the shrinking part, because that is also very important into actually getting usable testing out of your framework or your effort or whatever you want. Now, for this particular talk, I want to focus on that shrinking loop because I said that's what shrinking is. That's really what shrinking is according to QuickCheck, right? This is the standard that was created by John 25, 26 years ago now, and it's called external shrinking, right? Wait, what? It disappeared? Yes. So it's called external shrinking. And we call that external shrinking because, as we will see, the shrinker is something that is external to the generator. There's another idea, which is also popularized by Haskell in Hedgehog and Falsify, in particular, where, being a bit vague with terms, it's called integral, it's called integrated, there are multiple ways of framing, and there are different ways of describing the differences, but the high-level idea is that instead of having a shrinker, you are reusing your generator to make sure you're generating somehow smaller terms. Okay, let's take a step back and see where we are. So, as I mentioned, in Haskell, you have frameworks following multiple approaches. So QuickCheck follows external shrinking. Hedgehog and Falsify are internal, integrated. I'm putting them all in the same. That really should say generator-based shrinking, not internal or integrated. And obviously, if you go in other frameworks, you have similar frameworks taking opinionated stances. You have Hypothesis or QVIX QuickCheck that are internal or integrated. You have QuickCheck and others that follow the QuickCheck style. And a natural question to ask is, well, what should I do? For this talk, I'll obviously focus on the Haskell versions. And the question I want to ask is, as a user, how should I choose? And really, if you look at the literature right now, every time you come up with a new shrinking method, you go and implement a couple of case studies. You show that in those case studies, whatever you created is best. You ignore the rest, or you show how in the rest you don't do as well. And then nobody can compare the next tool with the previous tools because there is no comprehensive way of evaluating shrinking. And that's really what this talk is about, building the blocks for evaluating shrinkers and doing some preliminary experiments with them. But since I have 30-minute slot for an experience report, I'm also going to give you some background on shrinking to make sure everyone is on the same page and sort of explain what the differences between these three things are. Okay, so welcome to Shrinking 101, right? I can't do Shrinking 101 with well-typed terms. That is too complicated. So let's do an even simpler generator and property. This. So this is probably one of the simplest things you can do while still keeping something interesting. So what we do is we sample a random number, in this case from 0 to 6, and then we sample a random list by creating a list of that many elements with elements chosen between 0 and 9, right? Very simple list generator. And my property, which is totally non-trivial, is that the sum of that list is less than 3. And this setup is still enough to showcase the interesting differences between the different shrinking approaches. In order to do shrinking, by example, we need a counterexample. So let's pretend that we run our favorite framework and it found this bug, 3,6. Great, it's a counterexample. The sum of this list is greater than 3, so let's shrink it. First, we're going to shrink it in the style of QuickCheck. And the way I like to think about QuickCheck is we are going to make the counterexample smaller. We are going to make the list smaller. Now, that is usually achieved by writing some code that minimizes your types. For lists and numbers, that's already a default shrinker, so that's what I'm going to use, and in general, what I'm going to use throughout the talk. But the first thing that you might try here is, well, let's drop the head. Sure enough, I can do that, and it's still a bug. And yep, now this is my new counterexample. No matter what, I will start from this point again because it's smaller than the one before. It's a sort of best first algorithm. Then we start from here. Let's drop the head again. But now we are not in a bug situation, so that doesn't work. As I said, we're going to backtrack, sort of, go back to our locally minimal counterexample, keep trying. Okay, shrink the element. Well, the smallest number I can shrink it to is 0. Let's do that. No, the sum of this list is not less than 3. And then we go through this process of shrinking different things. Maybe eventually it will go to 5. This was actually traced. This is the order of things it happens, but we figure 5 is better. It will drop the head again. It will do more structural things. Might try smaller numbers, and then eventually it will end up with the actual smallest counterexample in this case. That doesn't always happen. And in this case, it's the list containing 4. So we went through this list. Oh, I had a very squiggly line going through things, but it's not visible for some reason. You go through all of these various counterexamples or candidate counterexamples and arrive at a minimum. What do you need to write to make this work? Well, in principle, you have to write a shrinking function. And the shrinking function in QuickCheck is a function from your counterexample to a list of counterexamples. So in this case, from a list of integers to a list of integers. The particular details don't matter. You can see that the first candidate string is drop the head, or you shrink an inner element, or the tail of the list. And that, in the limit, sort of allows you to shrink a list as much as you want. In practice, a lot of the time you don't write this kind of code. Someone smarter than you has already done that, and you get a generic arbitrary instance, which again is going to be the one that I will be using for the rest of the talk, because I didn't want to put effort into shrinking for this preliminary experiment. That's quick check in a nutshell. That's external shrinking. What about internal shrinking, or integrated, however you want to call it? Well, the idea here is that I'm going to generate smaller lists. I'm going to bake the functionality of shrinking in my generator, whether that is by making sure that every generator is accompanied by a tree of shrinks, which is the hedgehog way, or by making sure that I frame generators as parsing randomness, and then that I'm shrinking the randomness, which is the falsify way. In principle, however, both of these, for this example, they trace through the same sequence. And the idea here is that we are going to see how we can make the result of that first line smaller. In external shrinking, we didn't even see that n was generated, right? We just see the end result and operate structurally. Here, we are in internal integrated shrinking. You look at the inner results. So n is part of the things that we shrink, and we look at the first line. Is n 2? Well, we could make that 0. And there are ways you can adjust this, but the natural way you can make progress is, well, since n is 0, I will just keep 0 of the elements that were generated before. That can be achieved by reusing seeds, reusing randomness. There are some interesting techniques and a lot of smarts going into how that is achieved, but, well, the result is this is a candidate shrink. Nope, not a bug. Let's try again. Well, I could shrink n to 1. Good, I'll keep 1 from the previous thing. Still not a bug. Well, fine. N is 2, and then I'm going to shrink my list. And now it's sort of, we arrived at the same sort of place we were before, but we're not going to attempt to minimize the list itself. We're not going to go back and do a back and forth, because that's too costly. So in the end, we're going to end up with a list that looks at something like, okay, I'm making smaller and smaller candidates until at some point I hit this list, right? So I didn't get to as small a counterexample as before. That's not always the case. There are cases where internal shrinking will get to a smaller bug. There are cases where external shrinking will get to a smaller bug. So what's the difference? Like, why are people very happy with these generator-based approaches? So let's look at what you must write. Yeah, like in principle, the good thing about generator-based shrinking is you have generators, you have to write them anyway, so let's reuse all that effort and try to make sure that, well, users don't write shrinkers. There's another very good thing about it, which is that any constraints that your generators satisfy by construction are also satisfied by your shrinkers. But okay, let's take a look at this picture. Okay, there are different ways to implement this. The best way to think about it is that quick check is a function from a random seed to an A, and then you have a different shrinker, which is A to list A. Hedgehog style is integrated, which means you can think of generators as functions from a seed to a tree of shrinks, so each generator produces that, but then the bind behavior is weird. And then falsify, which came out a few years ago, is following what hypothesis is inspired by hypothesis, and what you get is generators are parsers from randomness, so whenever you want to minimize their result, you just minimize the randomness that was used to create it, and you get some nice compositionality that way, because you don't really have to lose information across binds. But in any case, that's a more technical discussion. So which one is best, right? That was the question I asked at the beginning. There's definitely a component that is user effort, right? You have to write something, how easy it is to make your shrinker do what you want it. I am not going to touch that in this talk. Like, that is a different evaluation than what I want to do. What I want to do is some more objective metrics and some visualizations for allowing us to reason about shrinkers in terms of performance. So for the rest of the talk, I will give two things. I will give you a background on how we evaluate some metrics for generators, and we adapt that setting to shrinkers, and then talk about a few experiments. Okay, so if we want to evaluate shrinking, we have to look at what evaluating generators does first, because they are very related, as we're going to see. And just to give you a bit of background, the evaluation that we're using, the platform that we're using, uses what is called mutation testing. So mutation testing is this idea where you start with your workload, your piece of code, and this is a vibe-coded STLC for some AST that you can probably figure out what it looks like. It figures out the type of integers, abstraction, application. This is the correct thing, hopefully. Here is an obviously incorrect version. I forget the guard, right? That's a bug, because I am allowing more things to have the type that they want. The idea behind Etna, the framework I'm going to extend, is that you are annotating, injecting these kinds of bugs throughout your programs, and then a generator is only as good as the amount of bugs it finds. So it aims to capture this ground truth of how many bugs does your generator find. And the reason I'm reusing this workloads, this framework, is because it already has a lot of workloads that we can use to evaluate the shrinking behavior. It has red-black division binary search trees. It has simply type lambda calculus and SystemF. It has some security-inspired information flow control ones. So it has a lot of these collections of properties, programs, and generators that we can just tag our shrinking behavior on and just evaluate things. The way they visualize generators, which will come in handy later when we talk about the performance implications of shrinking, is with what is called a bucket chart. So this particular bucket chart would correspond to 36 tasks, so 36 mutants that we would like to find. And the idea is that these 14 bugs were found in less than 0.1 seconds, then 6 more tasks were solved a bit slower, and then 4 remain unsolved, right? So this is a nice visualization to collect a lot of data. And that's sort of the standard that we also want to achieve with evaluating shrinking. So, okay, that exists. This work is about shrinking, not generation. So what do we need to do to extend this evaluation platform and this setting to support shrinking evaluations? Well, the first thing is, what do you measure? The thing we want to get to in this sort of ground truth way is, how effective is a shrinker? So how close to something minimal you get to? And how performant is a shrinker? How fast does it get there, right? So let's start with the first. How close to a minimal counterexample do you get? For this work, we chose to use tree edit distance. So we're calculating the tree edit distance from whatever your tool gave for shrinking to a minimal counterexample. That requires a minimal counterexample. We decided that we will find that via exhaustive search, and we used lincheck for that because, frankly, the previous paper showed that it's faster than smallcheck, so we used that one. Now, you can do this, and we went through all of the workloads that I showed you before with all of the mutants, and the shrinkers that we used were the default ones. So derive arbitrary for Haskell, and the default behavior that you would get for our hedgehog and falsify. So we didn't put any effort into shrinking, right? It's the default behavior that you would get. And the behavior, the data you get looks something like this, which is why we need very much better visualizations than what is here. And here is the visualization we sort of decided to settle on for effectiveness. So I'm going to spend a bit of time on this graph just to show you what it looks like. And the idea here is that the x-axis is tree edit distance to ground truth minimum. So you can think of that as, in order to go from the thing that quick check resulted in, as a counterexample, to the minimum, I need to do 10 edits or 20 edits. And the y-axis is the number of tasks that resulted in a tree-edit distance of less than whatever is on the x-axis. So top left is better, right? Number of tasks should be higher to make to keep a low tree-edit distance. That's the idea. The particular thing is that for this kind of evaluation, the shrinking behavior is very dependent on the generator behavior as well. So for this particular case, this was the SDLC correct by construction generation, but there are a lot more graphs on the paper that we can use. So I'm not going to show you all of these graphs because I don't have time. There's a lot of details in the paper. You can look at all of them. I'll just give you some representative graphs and some takeaways that I got and that we got while we were doing this. So here is one of these graphs. This is a type-based generator for one of the many things that we have. The thing is, most type-based generators look something like this. Hedgehog, quick check, and falsify sort of overlap. Like there's no meaningful differentiation there. And that's my first takeaway, and like half of the graphs that we created look like this, because if you are using naive generators, type-based generators in properties that have preconditions, they are not going to find interesting enough counterexamples to be able to shrink them. So the things that are valid if you're generating terms and hoping they are well typed are going to be small. So there's not going to be a lot of things left to shrink. In other words, if you are not putting effort in your generation, whatever you pick for shrinking sort of doesn't matter. Like, it's fine. What about other cases? So another one that I like is the one that I had before, which for most of the non-type-based generators sort of followed the same pattern if you ignore the quick check line. Falsify seemed to be more effective than Hedgehog almost across our benchmarks. Now, that's not me saying I want to only use Falsify moving forward. This is me saying that for these benchmarks and for these straightforward shrinkers, we get Falsify appearing to be better than Hedgehog. Great. The last thing is that as the complexity of the generators increases, quick check's external shrinking appear to be much better. It could do more. We don't have very many of these, so they might not be representative, but I still think that, as I was talking to other folks as well, this is also sort of folklore knowledge. If your generators are complex, the behavior of shrinking that is incorporated in them is going to be complicated enough that you need to put more smarts into it. You'll have to do something to the generator to tag the shrinker, whereas in quick check, you can, even a structural thing, if you have a very clear oracle, can work. Okay, so that's it about effectiveness. A couple of takeaways that I always show. And again, in the paper, those takeaways are powered by statistical tests. We have other metrics like sample efficiency. There's a lot more there. But I want to also briefly touch on a couple of other things. So first of all, shrinking performance. How fast do you reach the local minimum, and whether you affect generation performance. So for reaching the local minimum, we have a very similar graph. Again, top left is better, but now the x-axis is shrinking time per task. So how many tasks took less than some amount of time to reach a minimal counterexample. And again, way too many graphs, but the takeaways from these workloads is that quick check was much faster at minimizing counterexample. I did not expect that. And there is a weird crossing behavior that you can see in many of these, where as the bugs become more complicated, Hedgehog becomes faster than Falsify in reaching the counterexample. Again, this is just observations that we found. I'm not making claims one way or another. Finally, the last thing we have is generation performance implication. As I showed you in the beginning, quick check is a generator is a function from a random seed to an A. In Hedgehog, it's you are including the shrinking behavior there as a tree. And in falsify, you are also including some behavior as a parser. So here are the bucket charts. In general, they all look fairly similar. And the statistical thing that we got in the end is by making the shrinking budget 0, we figured out that, well, okay, QuickCheck doesn't have any performance overhead, but falsify is slower and headchook is even slower than that, which is what most of us expect if you've been in this shrinking area for long. Now, obviously, what I showed you has to be taken with a grain of salt, right? Were these workloads representative? They're standard caseloads that the literature is using, red, black trees, STLC, FSUB, but there obviously could be different in your case. Are the mutants interesting? Are the generators what you would write? Are the shrinkers what you would write? Well, arguably for the latter one, no. These were the default shrinkers, so if you put more effort into them, you'll get much better mileage. But before you even start doing that kind of exploration, like effort-based shrinking, where is better, where do I put my time, well, you need some kind of visualization of an easy way of accessing if it works. And that's sort of what we did. So it's the first thing in a line of, or the first step in a line of work of trying to evaluate shrinking and present visualizations with the hopes of figuring out what to use in your particular case. If you want to help us, well, that is already out there. Etna is extended with this line of work. You can add your workloads. You can figure out, it's very easy to add with the command line interface. You can add your own things, figure out if you are using the best shrinker for your particular case. And yeah, thank you, and I will take your questions.
Hi, thanks for the talk. Yeah, clearly there is no winner, right? So yeah, that's what I take with me. And I wonder if by looking at the generator, just at the generator, you could say, okay, for this, it's better to use falsify, headstock, or QuickCheck. Is there a hope for that?
So again, when I was looking at the data, pure data, I don't have a horse in the race. I didn't build QuickCheck, I didn't build headstock, I didn't build falsify, so I can show this data and not be too biased. That said, if you are focusing on purely generator performance, picking the framework that doesn't spend any effort during generation for shrinking seems like the obvious choice, QuickCheck, right? That said, if your runtime is dominated by your checker or by something else, then maybe it doesn't matter as much. And trading off user effort during building the shrinking with generation time is sort of a per task decision.
All right, thanks.
So thanks for a great talk, Leo. I just want to say it's really nice to see shrinking getting some attention because it's often underappreciated how important it is. You mentioned that Qubit QuickCheck has used integrated shrinking. And so this was actually a point that Kuhn and I weren't completely in agreement on. And you can tell which side I favored from the fact that Qubit QuickCheck uses integrated shrinking. But QuickCheck style shrinking has an advantage that you did not mention, and that is if you get a counterexample from the field that you did not generate,
you can still shrink it.
You can still shrink it, and that can be immensely valuable. So that's something that it might be nice to think about how to take into account in future evaluations.
That is a very good point. And obviously, there are many more things that this kind of metric-based thing won't take into account, some of which were, like I said, user effort in creating this, how easy it is to tweak a generator to support your shrinking behavior, because writing a shrinker is easy. Nobody does it, but it's easy. Tweaking your generator to make your shrinking better is much harder. Like there was this talk at ICFP by Anthony, I don't know if he's here, who was like, we cannot reason about whether shrinking is equivalent. And you need to use an arrow-based shrinking calculator. It's hard.
So in my experience, shrinking of randomly generated test cases is most important when your test cases are extremely large and then hopefully your shrunken test case is much, much smaller. Your edit distances are going up to numbers like 30, but like if you have a 30,000 line generated program and you would want to shrink it down to the like 5-line bug report, the edit distance is going to be somewhat larger. Obviously, that's
Depends on your edits. Sorry.
Obviously, it's more challenging to come up with like nice workloads and benchmarks for things that are going to be extremely large. But do you have a sense for what these comparisons look like at significantly bigger scales where shrinking is even more important?
So, great question. There are two things I want to say there. First of all, going from a 5,000 line program to a 5-line program is not the same, does not have the same scale as going from a 30-line to a 5-line program, because to go from 30 to 5 lines, you're sort of going to try deleting every line. To go from a 5,000 line program to a 5-line program, you're going to be deleting modules, right? So if your edit distance counts for a module change as 1, that's one shrinking step, you can sort of get that tractable. That said, getting representative workloads that are much larger than like system F sub, which is our, I think the biggest, like either system F sub or information flow control is currently our bigger workloads. The hard part there, I don't think anything with shrinking will suffer in terms of like being able to present the data, but being able to get statistical tests for generators in that range is hard. Right? Like, yes, you could do mutation testing over CompCert, but you would have to run each generator for 12 hours to find a bug. That's the risk there. If you have ideas for medium to large size case studies that are not type system, system F, sub, or CompCert, please talk to me.
Next, we are going to have Masaya talk about Haskell, interactive Haskell computing in a browser.
Yes, okay. Oh, wait. Perfect. Thank you for introduction and thank you for a great opportunity to give a talk here. I'm really honored to talk about the Zeus Haskells. It's one of the interactive computing environment of development. So first of all, this is a system demonstrations. This is a demo track. So if you want to working on that some examples, please open this URL or QR code. Yeah, anyway, it's a Zeus Haskells. You can Google it. So you easy to find it to open the Jupyter code. The origin is my research is a formal grammar research. It's not programming language communities. The time I would like to working on that is a categorification of the grammar theory. It's kind of mathematics sense. The time is one of the working example of the category theory is Haskell's. The time I would like to working on the reproducible example of Haskell's. One of the ideas, okay, I want to use the markdowns to write down to my note-taking to write this mathematics again. And also, I would like to use Haskell's learning examples. Then, the Jupyter Note is one of the options, like Python. The Python is one of the successful language in like Google Colab. Is that you working on that is a web server to access and download the Python package to demonstrate and it's a note-taking of the result. That times I would like to working on that in Jupyter Haskells to use. Then one of the good invitation from the data Haskells that is Michael is invited me that the community to working on that data science and Haskells. Then this is successful the development of the Jupyter Haskells. Then Jupyter Zeus community is invited me to the official project of the Jupyter environment for Haskell kernels. I know that one of the successful Jupyter kernel of Haskell is the iHaskell, interactive Haskell maybe. So this is a really fantastic features to visualizations, working examples, to do that something. But is some of the problem I faced. Then I'm working on that, the Zeus kernels to use it. In this year, hopefully to the Google Summer of Code to invite me to the one of the proposals. What about the integrate of the GHC? Yeah, in this time, before the submitting of the proposals, I used the micro Haskells. The 2024 is ICFP, one of the speakers to introduce of the really fantastic interpreter of the Haskells. I first introduced of these ones. But after that, in this year, one of the biggest news is the introduce of the GHC is working on that browser. So I would like to integrate of the GHC with Jupyter Haskell without installation. Yes, one of the reasons to why I would like to working on the Haskells in Jupyter code, I would like to lead over the category theory for programmers. The textbook is really fantastic to working examples. Yeah, of course I know this textbook is mentioned about the C++ too, but it's a Haskell example too. That time I'm working on that, but in this time is to use of the iHaskells. I have to use Brew installs, Paper installs, and GHC app setup to install the GHC installations. But sometimes the pre-built binaries doesn't available. I waited 1 hour or 2 hours to build up those GHC kernels. And it's a couple install the iHaskells again to wait with 1 hour. And iHaskell install the kernels in my home directory. Yeah, I don't have a tablet on Sunday because I just want to read the textbook. The time I think, okay, I would like to remove this barrier of Haskell. Yeah, yes, I know that is iHaskell is really fantastic, but it's too tough to just read the textbook. So the Python learner is just hey, open the Google Chrome and open the notebook. Just type the enters. You're easy to enjoy of your Python code. The time, no servers, no local tool chains, just a URL. This is a fantastic experience. No, this is my motivations to working on that. Why I developed the Jupyter Haskells in Zeus framework. I also sometimes working with the programming language community as a just teaching assistant, something stuff. The time is a teacher is, hey, Messiah, I would like to open to the Jupyter Haskell setup. The time, okay, so first homework is please try to install of the Haskells, please install the GHC app, and set up something. But hey teachers, hey lecturers, my Mac Air is working on the Intel architectures, so I don't working in the architectures that time, so we need to build up the Haskells, or I would like to use the Windows. Or it is so, we have no time to homework for working on. And also, instead, to avoid of the installations in a student laptop, that time I try to hosting of the Jupyter server using the iHaskells. This is also impossible. Okay, I working on that 3 hours to set up the Jupyter laptop, Jupyter servers, and therefore provide with the student. However, in Japanese community often to happen to the 30 student to working on the teaching of the programming language, something. That time, one servers to access the 30 student to the kind of untrusted code to submit. Of course, it doesn't work at all. That time, we need to separate to working on that to Haskell code to keep in the most strong infrastructure. Moreover, like in these situations, so we would like to share with my Haskell code to execute, but we provide the servers. This is untrusted servers, untrusted code, so this is impossible to use that. Then sandbox is really important to protect our security, and also provide a more strong infrastructure to working on. Our solution is that, yes, this is WebAssembly. Open the browsers, just provide us submit a static file. So no need to server, yeah, exactly, required to server, but it's just to provide a static file. Doesn't need at all. Yes, accepted demonstration is focused on the micro Haskell kernels. This is, again, this is a fantastic interpreter. Just read it, tiny C code to working on that is no dependency, just to type the make install to set up the everything. Oh, okay, thank you. The time is Zeus Haskell. I will explain later. So this is okay. This working on the C code, and the Zeus Haskell is also C++ framework. This is doesn't matter of the integration, just use the code of the C library to the Zeus Haskells. Okay. Should I do something? Okay, let me continue. The time, okay, the Michael Haskell is working on that is deeply integrate of the Zeus framework to communicate the Jupyter kernel between the Michael Haskell interpreters, easy to access of the internal dependency or internal structure of the data structure, like what is a variable, what is a function definitions. That time integrate is not so difficult to work. Yeah. I will show you the examples. So yeah, this is a Jupyter Lab image. No, this is exactly the iframe, so we can open it. Yes, the time is this is Zeus Haskell's is running onto the Michael Haskell's kernel. Maybe I spent the time to this ones. Then this is evaluate to this code to will be. Yeah, unfortunately, is a micro Haskell is required to compile to the combinators for every code. The time is the internal library code. This one's to spend the 1 minute to wait the initial startup. After that, it's easy to calculate this ones. Yeah, no problem. The time, yeah, this is amazing the working experience to Jupyter Haskells. Yeah, you easy to embed of any Haskell notebook in your HTML slide. So this is because of the minimal dependency of runtime, including the microcontrollers to working on that. So I used the EM scripting to compile to all of the kernel into the WebAssembly. This is self-hosting, is a no dependency, is a bootstrap itself of the C compilers. And also fantastic sense is Haskell is compiled into the C language with combinators. The time, yeah, Haskell code to C code to WebAssembly. We can realize to any Haskell library into the WebAssembly to library. Yes, this is the end of all of the I accepted demonstrations, but as bonus is a GHC WebAssembly thanks to the Google Summer of Code and my mentee of the Arman. So this is working with the GHC WebAssembly stuff. First, we compile to the GHC interpreter, GHCI, into the WebAssembly to communicate with interpreter between the JavaScript. So this is also successful to working on that any I/O states and function definition any variables. Everything is inside of the WebAssembly, working with Jupyter kernel. Yes, the brief of the example of the why GHC is working in browser. GHC is the front end live coding of the GCI introduced in the 2025. The GCI browser is hosted the WebAssemblies is with options. The -F is the GHC browser options to compiler. Client-side compiler is and type check and the bytecode interpreter is everything inside of the WebAssembly. This is fantastic. The in-browser GHC file systems. Yes. After the releasing of the Jupyter Haskells, some of the communities asked me that why not you use the GHC? Why not use the GHCI in browser or something? Yes, I know that, but it's too tough work to communicate because Zeus Haskell is working on the C++ that should be compiled into the C code. But it's thanks to the GHCI is written in Haskells, I have no idea to communicate, but it's in this time I can do it. So the time is this is the GHCI, GHC kernels. This is the latest version of development. Of course, this is more faster than others because compared to the micro Haskells, GHC is just compared to the more efficient bytecode interpreter and the cache it with the file system. Yeah, of course, it's everything inside of the web browser file system. You can use it as any GHC extension, any GHC standard library inside of the Jupyter kernel. Sorry. Yes, that is all of the thing of my demonstration, system demonstration. But I still have 10 minutes to explain to my internal structure or more technical example of the Jupyter kernels. And maybe in further, you might want to interpret your Haskells inside of the browser. That I'm really helpful to information for you. And also this is you may face some problem in the future because the Jupyter Write. So this is the Python, but Python is compiled to the WebAssembly, and the Jupyter is compiled inside of the Python interpreter running on the Jupyter kernels. I mean that is you need to first you need to know the Python to working on the Jupyter Write. So this is a static file and the deploy of the Jupyter kernel into the browser and working with the web workers. This is isolated, so you cannot access of any DOM object into using the Haskell. And also, the Zeus is a separated project. So this is, I'm not sure about that, but this is an independent France company to develop it. Zeus is a C++ implementation of the Jupyter kernel protocol. So now you need additions to the Pythons. You need to know to the C++ to implement of the C++ code to Jupyter kernels. So this is a notebook or console or Jupyter Write is like the web applications. Everything is that you can use the Zeus framework to communicate with the Jupyter kernel. Then I linked of the Zeus Haskells into the micro Haskell, GHC, and maybe in future it's your runtime. The architecture is quite simple. One of the notebook front end you saw that is in browser. That time is shared Jupyter layer implemented by Zeus and called to the Haskell kernel. This is a micro Haskell is again, this is a C library, just to call or the WebAssembly code directly to function call. It's fine. But GHC WASM is different. So this is a WebAssembly. So in addition to the Python, C++, you need to know JavaScript because of the communicate with Haskell to export of some functions. JavaScript call it is the functions, and Zeus Haskell is a C++ called the JavaScript function. So that time is a 3 time or 4 time to data structure is converted to each native languages. That is so tough work to working on that, but it's did it. So that time is this is trade-off. The micro Haskell is really simple, easy to embed to the C libraries, the native and the browser. So this is can be work with any C library is can call to of course is the native like ordinary computers and also browser. But the JC Wasm is of course this is WebAssembly. Yeah, recently working on that as a native side, but it's, anyway, the Zeus Haskell is working on only the browser and the communicate with the full language. But it's a compatibility is very high. Backend is we sell to the request to the what is the code to execute. The level is update of the states, and the result is a IO monad or something, and it's show to the any example. That time is a cell is just to send of the square and the map of scale to 1 to 5. Then this is everything is inside of the single files, and the compile it and execute of the only to the last monad result to show it. Thanks to the Haskell is a static, purely functional, purely static language. That time, so state is doesn't care about that. Is every time it's compile again, and then every time is consistent to show to the result. GSC is a different backend. The Jupyter-Write, the JavaScript ones, and the WebAssembly workers to communicate. This is a bit different because the cell is an input of the code. That time we interact with the GHC interpreter. So GHC interpreter internally call to the run declarations or execute statements, some functions to call it, to translate it by line. And the lastly is we remove any monad wrappers and just print the value of the last ones. So the Jupyter kernel has a 2 kind of option of the model. Is a really monolithic version. Is a Zeus Haskell is a deeply to integrate with the own interpreter. So if your interpreter is implemented with C, luckily very easy ones. But as your Haskell interpreter is implemented with some another language, this is maybe tough work because you need to communicate with JavaScript again. So this is control of the state is also hard too because no way to access the internal structure. That is almost the everything of my talk. The internal semantics has different ones. This is a declaration. Declaration is just we keep in the states, just evaluate it every time. But the expression is show the result. So without state any update, doesn't happen. And the IO action, like is a print monad, is the execute of the what's once, and the state is changed. So this is we need to care about the 3 kind of the data in Jupyter kernel is carefully to deal with the consistent result to Haskell. Of course, the iHaskell is a really impressive work with the data visualization. Of course, it's Python too. We have the table, we have the graph. So of course, our kernel is also do that to send with that, like the main type is text LaTeX and any LaTeX code. The time is evaluated the mathematics sense, execute of any sense to show that anything. So before concluding of our work, I would like to thanks to the first is a Google Summer of Code, and the one with the mentee is Arman. So without their help, I cannot start with this project. And thank you for the ACM community to travel grant. Really happy to honor to join this community and attend the really exciting keynote and the presentation. And Haskell organizers, yeah, really thanks. So because I have no enough budget to come here from Japan, that I am really helpful with that grant. And also our research grant community, thank you, and the ChatGPT.
Struggling a lot with like students installing environment, and the first wave is essentially all that. Like I'm listening with that a lot. But do you imagine like at some point they will start like changing from browser environments back to like the environment, or like there's also like the ecosystem with Stack and the Cabot, etc. What's your take on that?
I see. Thank you for that time. Yeah, of course without the servers, that is a problem. So we need to care about only the browser is inside of everything. Sometimes the portability is some sensitive to hard. That is one of the points. I agree that. Thank you.
Hi. Can you say a bit, maybe I missed it, but about how you use this in your work? Like you talk about being a formal grammar researcher and teaching. It's not, I just want to hear more about is that, I mean, surely your grammar is bigger than that. So yeah, or what do you have, I don't know, maybe some kind of parser happening?
Yes,
that people...
parsers, exactly. For example, our community, like, this is another work, but is,
Yes.
yeah.
How's he doing?
For example, this one's, yeah. So
yeah.
This is a combinatory parser of the Japanese community to working in this ones. This is dependent type presentations to working on that. But this is written in Haskells. So the time is, we need often to use the Haskells to develop the parser too.
So are you running this inside now and people use it? You can try out demos during, I don't know, S3 tutorials.
S3 tutorial, yes, exactly.
Yeah? Oh, really? I was just, okay, really? Okay.
Yes.
Oh, good
yes, that time is my favorite one of the paper I would like to introduce you to the
categorical and categorical grammar. Like, what is there a browser? Like, if I wanted to advertise categorical and categorical grammars to someone I meet here, is there a URL I could show them?
Sorry, at the time is really private ones, so I can't do this one. Yeah.
Okay, all right.
Hi, thanks for the talk. So you were a mentor for Google Summer of Code for Haskell, and I noticed that you had like several projects and at least one mentee. And I was looking at the Haskell Summer of Code project ideas, and one of the things listed here was like one of the challenges was running libraries on compiling libraries to micro-HS, and one of the things that you wanted to do was this feasibility study that would identify libraries that could be realistically compiled to micro-HS. And so I was wondering if you had any success with that, and maybe you could speak to what the challenges are on supporting the whole Haskell ecosystem on this minimal Haskell implementation.
Yes, thank you for the questions. This is a really important question. The library bundling is a success. So we can use any library in Jupyter Code because of the static libraries in the embed of the EM scripting file system, just a port of the inside. Then you're easy to call of the library in micro Haskells. That time the library is possible. However, the package access is a Haskell, the package is hard problem. And also, this is Haskell community, so I would like to call for help. That is, a web browser has security reasons to hard to access of the Haskell package indirectly. So the package server is, of course, the security reasons to the block of the direct access from the browser. Like the card or widget, we can do that, but in the browsers, this is security reasons, is protected, is a CORS blocked. The time, indeed, we can do that with the web browsers with if package is just admit of the Zeus Haskell domain, then we can access of the download of any Haskell code, then compile to the micro Haskell. This is theoretically possible. And also, EM scripting system is we already ready. Just as one of the issues is network access in the mind.
All right, our next talk is Alessandro on turning parser errors into suggestions for REPL.
Yeah, I think I give away my age. Yeah. All right. Thanks. Let me start this talk to share some common frustration that sometimes I have as a developer. Here, we loaded one of the most used databases, and imagine that you do this not every day. You do it like sporadically. And I want to, get out of this system. It's a system that, provides a prompt, and I need to put some commands, right? So I say exit, something happens there, semicolon maybe, no, error. So maybe quit. No, I press tab, shows the folder, no autocomplete, right? So is there any SQLite expert in the audience that tell me how to get out? No, Control D, no, kills the, in a graceful way, All right. So it's like .quit, right? So, but this is showing you like there are many systems out there where, you don't use it regularly. You get in, there is a prompt, and you want to know what are the commands, and there is no autocomplete. And that Satman said today, developers love autocomplete, right? And it's 2026. So, we face this problem in my company. So we have a company called Dipela, and we develop our own DSL. So imagine that, established tools, they don't have autocomplete. Imagine about DSLs that we create all the time, right? So, we provide, you can see here the language, quite literally, you can understand what is going on. It's related to databases, so yeah. So you can see, pretty good, right? So still, when we give this to people to try it out, they are in the same problem, right? So they start with a REPL, like this one. Let me just put it here, right? So yeah, and they're in the same situation as before, with the exception that you press tab now, and you can see the commands, right? So you can say like show, and it tells you data sets, right? It shows healthcare, okay? You can say, well, let me sample from healthcare. See, something wrong over here. Okay, let's roll back, sample data sets, now completes healthcare. You see how it's helping me out to discover the commands, right? Run the command, yeah. And you can see that, we did a sample on the data set. And I'm going to show you in this talk is how to implement this autocomplete with minimal effort, right? So since my company is a startup, you need to cut corners, right? And sometimes cutting corners leads to innovation. And yeah, this is what I'm going to show you today, okay? So let me switch back to as it was before. Um,
嗯。 Um,
There we go. 嗯 There we go. 嗯 Um, 嗯 There we go. 嗯 Um, 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 嗯 So yeah, so this is a joint work with Matty and Elizabeth that are working at the company. So yeah, I show you the problem. We have a prompt. What to, what is the command to write next, right? So yeah, as I said before, many DSLs, they do not have this autocomplete, and we want to solve that problem. All right, so I did the demo. So yeah, I will skip that part. So to understand, have 22 special syntactic categories, and we will see what they are. So it's quite, a beefy example, if you wish. And just to be clear, in the scenario that we are, so what we call a REPL-driven DSL, right? So imagine you have a DSL that runs in a read eval print loop. Essentially, you have a prompt, and there is a system where you put an instruction, hit enter, does something, and then the next instruction, and so on. Okay? So this is the scenario. The cursor is going to be always in the end of the line, right? We don't need error recovery, so it's not like in the compilers where you detect an error and you continue parsing, right? So here it's like one error only. Yeah, and there is a session behind the prompt. There is an state, something in the tool that has some state. Right, and if you take something from this talk, it's the following. We realize that many of the tools out there, many of the parser tools that we have in Haskell, when there is a parser error, the error, it tells you what you are expecting. And what we did here is like, okay, let's convert that, it's a very simple idea, into suggestions. See a parser, the most traditional one, it's a monadic parser that after perform the parser, returns a command, and the command says, is grant role, and then you describe what type of role you want to grant to the user. Administrator is a data analyst or a data curator, right? And then keyword 2, and then you say account handle, which is the username. All right? So when you do that, then you return the part of the AST, grant role with the role and the handle. Okay? So that's the parser, that's the grammar, that's what we have in the system. Okay? All right, so I'm going to show you how we do the autocomplete in 3 steps. Well, 3 different steps. We start with the most simple one, which is suggesting keywords. So then, next time I want to exit the system, I know which command to run. Right, so yeah, and I'm going to show you the autocomplete, and I'm going to explain you, because, just this kind of, these lines that you have here. So the first thing to notice here, we have something that says expected token. This is a data type that will be the suggestion, right? That's the second argument of this function, and all what is before is the first argument. This is a typical, line and word division that, for example, Haskell line in the Haskell ecosystem is used to split, a prompt in that way. The word where you're writing and the rest and the line before, right? So the first argument is the line, and the second one is the word. Then we parse the line, and if there is no error in the line, we are fine. But if there is an error, we need to do some suggestions, right? And we show some examples. We need to do some suggestions. And here, it doesn't matter much of details. The important thing is like you extract the expected token from the error. You make those suggestions more beautiful. In this case, span suggestion is trivial. It just doesn't do anything. Just keep that in mind. And after you extract the suggestions from the error in the parser, you check which of those suggestions makes sense for what the user was writing. Okay? So that's the pattern. Extract what the suggestion from the error in the parser, beautify them if you need to, and then check which are valid. Okay? And the ones that are valid has a condition there. It's a little bit weird, but I will explain you that in a second. Yeah, and with that, we already have keyword suggestions. So if you remember the parser I showed before, you say grant role, you press tab, and it will tell you admin, analyst, or curator. Okay? And you have autocomplete for keywords with 12 lines of Haskell code. Okay? All right. So let me guide you through this suggestion. One, a suggestion is valid, which is like this condition we have here. So there are two things here. The error needs to be in the end of the line. The end of the line is, but it's not doesn't contain what you're writing, the word that you're writing. It's the line, just before what you're writing. And the conditions say the error should be there, and whatever suggestion you get should be a prefix. Sorry, what you have currently writing, in the last word you're writing, should be a prefix of the suggestion. For example, if we have this GR and you press tab, what happens is like here the word is GR, and the line, what is before, is empty. Right? So there is an error in the empty line. Say, this is an empty line. I'm waiting for create, grant, and show. Right? But I'm only going to provide grants because GR is a prefix of grant. Okay? So then the error in the end of the line, so this is a different one. So here I have grant role, I do one space, and then I press tab. So here the word where I'm sitting on is empty, and the rest of the line is grant R or L. Here the error happens in line 6, because it parses grant and then fails because there is no role written R or L. So in this case, we don't suggest anything, because the error needs to be in the end of the line. We don't repair. We don't do reparations. This is just, needs to be an error in the end of the line. Okay? So now you got how to do keyword autocomplete in 12 lines for your DSL that you're going to create in the future. But we can push it forward even further, right? So let's go one step more. That we realize, when people were using our system, the command. For example, you say, show account, and then you want to tell them, here I'm waiting for a username, right? So this is what we call suggesting syntactic categories, special syntactic categories. Right? So we want to say to the user in the system, show account, you press tab, and say, here you should write a username from your system that is connected with the state of your REPL. And for that, we use labels. Labels is a way to label a parser. This is megaparsec allows that, and many other parsers they do as well. And when there is an error in the parser, the error will include that label. Okay? And we repurpose that labels just to show the user, here comes something that you should input that is related with the state of your system. It doesn't come from the grammar of the parser. Right? And this is how you do it. You say, for example, account handle, the username. You put label, account handle, and then says this is an identifier, but it has this label. And then you can take many identifiers and put different labels to tell the user different things that they might enter. And with that, when the error comes, right, so it will be included in the error message. And then you say show account, press tab, and it will say account handle. Right? So it's one of your users. Okay? So that's extremely simple, but extremely useful for people facing your system for the first time. And it's just about going in your parser and put label here and there. That's it. But we can go one step further. And why don't the REPL suggest what are the users that are in the system? Right? Instead of the user thinking, oh, I should remember which are my users, the REPL should provide that information. Right? And this is exactly what we did. And for this, we need to use something that is not in all the parsers, but is in megaparsec. In megaparsec, errors can have, there are some special errors in megaparsec where you can put any payload that you want. So the payload that we're going to put in the error is like the command to run to obtain the suggestions. Okay? So, yeah. Sorry about this. This is, I forgot, sorry. I was already in one step further. Sorry, let me roll back a little bit. This is about the categories. This is how we need to adapt the code for the completer. It's the same as keyword, except that the word needs to be, for the category, needs to be empty. You are not writing anything. That's the only difference. Sorry about that. Let me go to that's the context-aware suggestion, the one that I was talking about. yeah, so now we want the REPL to provide the suggestions, right? So the way that we do it is like this with a combinator called label with command, that you put the label, but then you put the command that it should be run to obtain that suggestion in the case the parser fails. And here is like show accounts. Okay? So same idea as label as before, but now the REPL will run the commands and you can get the suggestion back. All right? So, and here is where, remember these beautifying things that I will show you in the completer, that you extract the information from the error, you beautify them, and then you check which are valid. Here where things get more interesting, because now the beautifying part, the error the error in the parser will have a command, and the beautifying thing means run the command, give me the suggestions. Right? So, but because I need to run a command, I need to do a lifting of things into a monad. In which monad? In the monad that the REPL is using, whatever that is, right? So here, the beautification of a keyword or a category shows we add return, the span suggestion for commands, then I need to execute the command. When I execute it, I get the suggestions, and I return them as keywords, right? But if I run the command and nothing comes back, I will show the label. Right? And this is the list command. I mean, the suggestion is a command, and when you print a command, you print the label associated with the command. That's it. Okay? And when this is valid, a suggestion is valid, again, as before, as categories, you need to be in the end of the line, and you are not writing anything. Right? So then you can write show account, tab, and then you get the list of usernames. Okay? Right, so we need to lift the completer to be monadic as well. So in the blue lines, the blue color lines is the completer I showed you before, but now lifted to a monadic computation, right? So the difference, like the return type doesn't return a list of string as suggestion. It's a monadic computation that returns a list of suggestions, and it takes one argument called execute command that takes a command and returns a monadic computation with a maybe list of strings. And then you pipe it through. It's the same as before. Look at the error, beautify the suggestions. That means run commands if you need to, and then check which are valid. And that's it. That's the autocomplete. Okay? So one more other things that we found useful that will help you when you design your own DSLs is like sometimes it's good to distinguish when new identifiers or things are related with the state of your REPL and when the user needs to provide new information. So for example, when we do create account and you press tab, the user needs to provide an account there, right? So it doesn't come from the state. So then we put a special label that say new account handle. Otherwise, as I showed you before, show account, you press tab, and you get the username Mitrandri and Pippin, right? So yeah, in one you use the label with command, in other ones you use label. That's it. So the whole autocompleter, if you look at the paper, it's around 55 lines of code. We didn't modify the grammar at all. We just add this label with command. That's it. Yeah, for the special, and then you need to add this label for any special category that you want to show the user. All right, so when we got previous reviews on this paper, people would say like, oh, but this is, does it scale to other languages, and it's only a Haskell thing. Here it's in the Haskell Symposium, right? So nobody will ask that, but so we did some experiments with Python, Rust, and Scala, and you can see there are different parser names. And we also enumerate what are the feature of those parsers libraries that you need to implement this technique, right? First, it needs to be a parser combinator library. It needs to, when there is an error, it needs to tell you the expected tokens. It needs to handle labels, and when the error happens, the label is included in the error. And it needs to allow, arbitrary payloads so we can, put the commands to run in the REPL. But the last point is only 4 megaparsec. How you hack around that when you don't have that? In the label, you encode the command to run. It's horrible, but, you know, and then you have a dispatch table, but it works. Okay? Okay, some limitations about this, because, you know, this is a very cheap way to get autocomplete, but it's not perfect. So one of the limitations is like sometimes you have like combinators which are based on Haskell expressions. For example, this one, satisfy, give me a character and tell me if that character is in a list of characters, right? We cannot introspect a pure Haskell function there. So if that fails, the parser will say this predicate was not fulfilled, but it will not tell you why, because it cannot go inside the Haskell function. So there, what you need to do, instead of writing it like this, you need to write it with combinators. And there will be a trade-off between efficiency and autocomplete features. So optional arguments. Sometimes some commands, they have optional arguments. How do you notify that to the user? Because, you know, if they're optional, there is no error. This is a valid command. So what we do there is like, even if there is no error, we inject a character that will trigger an error, right? And then it will tell us, you know, we are expecting these optional parameters. So we need to induce the error to show additional parameters. And we do that in the implementation. This is very syntactic and very cheap, but, you know, it would be nice to be more semantic. For example, if you write from the table people, select 30 bigger, and you press tab, we will show you columns from a given data set, but it will be good to show you columns which are related with numbers, because the other ones don't make sense. Okay? And as I said before, we deal only with an error, and it's in the end of the line. Some future work. I show you a very simple technique, an insight. Can we package this in a library so that, you know, you import the library and you get autocomplete in your DSL automatically, right? Here, you know, you saw the few lines, 15 lines of the autocompleter, and the label and label width, and that's it, that you scatter in your grammar, and it's done. How we package that to be a library? It would be nice to have autocomplete when you have bindings. So now at the moment, we don't do anything with that. So you're writing your command, and you want to refer to a variable in the same command, but then we don't consider that. And this same autocompleter, we wrote a language server that runs autocompleter, and then you can be in visual code, and when you write, in the end of the course, you see the suggestions. Right? But it's a little bit rough at the moment. Right? Yeah. And I think with that, yeah, I conclude my talk, and happy to take questions. Thank you.
If you have question, please come to the mic.
Hey, nice talk. I was wondering, when you're already including some combinators for affecting the behavior of the completer only, like label. Could you do something like that to affect satisfy, right? Like a combinator for saying, okay, I know that you won't be able to introspect this particular parser, but I would like the autocomplete behavior to be the CS, the list of characters that I was expecting.
Yeah, but, it's kind of hard. It's hard for me to see how a combinator, because a combinator will take a pure Haskell function, and then you need to introspect it.
No. I was thinking more along the lines of I would add user, I want you to, if you were to introspect this satisfy, you would have gotten this thing that you were expecting. So just explicit user tagging of what to expect at points.
Right. Not sure, but we can, yeah, let's discuss. I haven't thought about this, to be honest, yeah.
Hi, I'm not sure why you said that this will only work in a repo setting. You said with a file, or if you're trying to complete in the middle, why not just chop off the rest and just complete the prefix? Is there a difference?
I mean, it's, all right, yeah. So it could work, but you know, there is I didn't mention, but there's a lot of related work about how to do this auto-completion for, full files and so on, and people have done a lot of research. And I will use something like that instead of using this. Because, we fell short in many, we could do what you say, but I think I will go more for like full feature techniques for autocomplete in files.
Okay, so it's about features. But if this still will give you a solution.
It will give you something, but it doesn't deal with binds. It doesn't deal with many things that.
It doesn't deal with what?
Binds. So it will not see variables in your scope.
Oh, okay.
Yeah. So there are certain things that other solutions are more.
So it's just that longer programs tend to have the kind of things that call for additional features. Okay,
yeah.
Got it.
Yeah.
Hi, Alejandro.
Hi.
Thank you for the great talk. I was thinking about that example that you showed at the beginning where you were trying to quit the SQLite
Yes.
REPL, and you tried quit, but that didn't work because the command was :quit. And I was thinking, so with that autocomplete is not quite what you want, right? Because the command you want begins with something different than the command that you typed. So maybe there what you actually want is more like spell check for your commands. And I was wondering if it would be easy to integrate something like that. So I guess this is a feature request.
Yeah, so I mean, in our tool, for example, when you press tab, it will tell you quit, and then you know how to write it, right? So
Okay.
yeah,
So
it works as well. I mean, yeah.
But it would, I guess, if you haven't typed anything, then your tool will show you every possible command.
That's correct.
I see. Okay.
Unless you look for, but even if you type Q and you press, it will complete quit. But that's what you say. You need to know that you need to start with a special character.
Right.
Yeah.
That said, I still
Yeah,
think spell
that's-
check would be a cool
Yeah.
feature if it were possible.
I haven't thought. Yeah, cool observation. Yeah.
Okay, second question. So when you're trying to complete like an account name, I was surprised to see your valid check to require the word already typed to be empty. Because it feels like if I type a prefix, right, like you have two account names, I think someone M something and P something, and if I type M and I hit tab, right, I kind of just want that to complete to the rest of that account name. So I still want completion, right? And relatedly, suppose there's two names that start with M. Like suppose I finished typing an account name, but actually I want to even long. So like suppose that one account name is a prefix of a second account name, right?
Yeah.
So I was wondering, because you talked about this trick where you add a very bad token at the end so that things would not parse. But here it would parse, yet I want to access the even longer completion.
So yeah, actually in the implementation, we changed it later on. So you are right. So you say show data set. This is what you say, data set, right? So and then it looks healthcare, and it does. Yeah. But
what if you have a second data set that's called healthcare final?
I don't know.
So
I don't know what in that case, I think I cannot try it, but what it should do is like show you both of them. But do not complete.
Yeah, because this one already parses is my
Right.
worry.
Yeah. So here the adaptation that we need to do in the code, I show you, the word needs to be null. Here you need to say the word is a prefix of whatever and that's it.
To answer the quit question, if you were to move to something that supported island parsing, I think you would be able to get quit because you don't have to start at the beginning. And I do think there are some ways, this is speculation, I suppose, but I do think there are some ways to convert parsec to do island parsing.
Okay. Yeah. Okay, good.
I hope it's a very quick question. I see that your autocompleter is a monad, but also there are a lot of parsers that you can write with applicative functors. Have you looked into if you really need monads or?
No, we didn't look into. We didn't look into that. In some part of the parsers we use applicative, but no, it's something we implement all of this, as I saw a lot of constructor and so on, we just implement it with Megaparsec.
I'm just super curious about that. Yeah.
I haven't thought about it.
Yeah. All right, let's thank Alessandro again and Sam. And thanks to our speakers and student volunteers, and yeah.
people are leaving instead of coming.
If there's anyone else who'd like to leave before Leonard's talk, this is your time. All right, welcome to the first afternoon session of the Haskell Symposium. We're going to lead off with Leonard Augustsson, who's going to tell us about how to get the best of Erlang in micro-HS.
Hi. So I will start by saying that this work has been done to 95% by Robert Krook, who couldn't be here because he has a young child. So I'm here, and I will blame everything on him. So what is Cloud Micro Haskell? So quite a while ago, there was something called Cloud Haskell, which I will describe in a moment. And this is just a re-implementation of Cloud Haskell using the Micro Haskell system. So you can, with it, you can get easy distribution of Haskell tasks that run on different nodes, different computers. And it was built by Robert using standard Micro Haskell. No extensions were needed. And just to show that it actually works, I have 2 computer systems here. And they're connected by an Ethernet cable. I don't know, this one has a little green LED. Can you see that it turned on? And you can turn it off again. Amazing. This was just to show off that you can run this on fairly small systems. Well, I mean, this system is enormous. I'll go show you later. I mean, it has 768K of memory, so. So what is Cloud Haskell? So now I'm just going to recap Cloud Haskell, not anything about Cloud Micro Haskell, but it's sort of basically the same. It was Haskell 2011, I guess it says here. Jeff Epstein, Andrew Black, and Simon Peyton-Jones had this paper. And it was kind of an attempt to recreate Erlang-style API in Haskell. And so simplified, here's some simple example, something that actually doesn't work in Cloud Haskell, but to give you an idea. You can send to some process something to do. Here it's a function you're sending. We'll come back to this very example later. So what do you have? So you can have a machine with different processes, and they can talk to each other, and then you can have a second machine, and you can talk to that across a network boundary. And you don't really need to know where the thing you're talking to is. It looks the same whether you're talking to it locally or you're talking to it remotely, which is very nice for sort of this kind of programming model. So this is very, very Erlang-y. So the basic primitives that are important are send, where you give it the process ID, and you give it something to send, and it does that. So you're in some monad process M. And you can say, well, I expect something. I expect an input, and you get something back. And you can take one of these processes, and you can spawn it on a different node. A node is one of these computer systems. I mean, it could be running on the same machine, but it's sort of an independent entity. There are many more, but these are the important ones that we will look a little bit at. And so this is the Cloud Haskell API, but not quite, because you can't really send anything in Cloud Haskell, so you have to make it a little more complicated and say, okay, I have to make it a closure of something to be able to send it. I can't just send an arbitrary thing. Closures can be serialized, but not arbitrary functions. And so to do that in Cloud Haskell, there is a whole mechanism where you can, some things can be turned into static things, which means that they can be represented by just some kind of internal pointer rather than being code. So you can make a function static if it has no free variables, sort of. So top-level things can be made static. And then you can make it back into its original thing. So the idea is that you can make something static, and something static is just some kind of identifier. You can send that to the other side, and they can unstatic it and get back the actual thing. So the bad thing about this is that you kind of have to run the same binary on both sides of this, the sender and receiver, because this label you're sending over, it's just sort of a pointer to some bit of a machine code. And it had better exist on the other side as well, otherwise it won't work. So it makes it more cumbersome. So here is this simple example again. You want to send this function that computes x plus y plus 1. But that function, the function that you want to send, lambda y, it has the free variable x. That means you can't send that. You have to make this. What is this? Well, the thing you can send is this sfun. It's a function you can make static. And so it takes the y, but it also has to sort of, it will get an encoding of its free variables, so you have to decode that byte string into the x, and you can add them and so on. And since sfun doesn't have any free variables now, you can make it static. So you can make a closure that has a static function, and then it has some free variables that you have to encode. So this is, let me say, I don't think Cloud Haskell ever got very popular. So this was mitigated by having some template Haskell stuff to make it easier, but still. So you never send functions over the network. You send these kind of identifiers, and they must exist at the other end as well. Or at least, I mean, it doesn't have to be exactly the same binary, but it certainly has to have that same identifier. Okay, Cloud microhaskell is slightly different. So here is this function again. So if we have Cloud microhaskell, what do? Nothing. It just works. Maybe it doesn't quite work the way you think it should, but you can send this thing, because you can send arbitrary things over the network. Well, I'll get back to that in a moment. Almost arbitrary. So here is the difference in the API. So the bottom one is Cloud Haskell, which has this serializable constraint. And the thing that you spawn has to be a closure. Whereas in Cloud microhaskell, there is no constraints on the A, and you can just spawn any process. So there's no extra cumbersome layer of creating closures and so on. So here is a simple example, and this would look similar in Cloud Haskell. So you have a data type, ping and pong. So the example, so self gives you the process identifier for this process that's running. This is all in the process monad. N gives you the node that it's running, the computer it's running on. And we want, in this example, we want to start a computation on a different node. So nodes ask for all the nodes, and then I said I wanted to start it on a different node, so the filter filters out this node. So now I have a list of other nodes, and hopefully there is another node, because then I take head of that list, so it would crash if there were no other nodes. This is a simple example. So n prime is another node, And then I can just spawn something on that node. So on n prime, I spawn something that calls expect and hopes for a ping, otherwise it will crash. And then it will say that it got a ping, and it will send a pong back to S, which is the process ID of the thing that runs here. And notice that you don't have to sort of figure out that you're sending this to a different node or anything. You just know it has a process ID, and they are unique over the whole system. So you send to S, and then the parent then, it will send the ping to the child, and then it will expect to get the pong back. And then it's over. So to anyone who knows Erlang, this is nothing strange. Cloud Micro Haskell has the same sort of things as Erlang. You can monitor processes. So here, child, you spawn off some process, and then you spawn something that will monitor this child. So it says monitor trap exit child, which means that if the child dies, then this process will get the message saying process died. And then it will print the message there. You can also, like in Erlang, you can create linked processes. So this linked one, it will connect itself to the child with this monitor succumb, which means that if the child dies, then this linked process will also die. So there's no sort of invention here. This is just implementing cool stuff from Erlang, which I think is fantastic for these kind of things. And this is another thing borrowed from Erlang. They have this notion of a generic server where you can say, I want to set up a server, and there's sort of things. How do you handle the setup? How do you handle the teardown? And then there are two things you can do to a server that runs. You can call it, which expects a response, or you can just tell it to do something. And this ST argument that you have here, it's the type of the state that is internal to this process. So it will handle one call or one cast, and then will wait for being told to do something else. And the generic server infrastructure will make sure that it just keeps going, and it handles a call or a cast, and then keeps going until it's told to tear down. And there are lots of type parameters to this data type, because you have the type of the internal state, and the request type, and the reply type. Why is cast and request call are different, yeah. And then there are some functions down there that sort of call and cast that says, okay, I have a server, I want to execute a request, which is a call or a cast, which is the one that either expects a reply or no reply. Here is a simple use of this. The only reason I'm showing you all this stuff is that the thing that's running on these boards is a generic server. So you have an idea of sort of what's running. And I'll show you the code that's running on these boards in a moment. But since they're using this generic server, it's sort of good to see what it's about. Okay, so we want to make a little server that is a counter, and it will have one type of requests that expects a reply. You can say get, and that will return its internal state. You can see the handle counter call. The first thing there is the type of the state, which is an int, so it just counts. And then if it gets a get request, it will return the state that you asked for. It doesn't modify the state, so it will return the unmodified state and a reply. And the cast will do different things. If it gets increment or reset, it will add 1 or set it to 0. And then you just say, okay, I want to make a server that has setup, doesn't do much, it just starts the initial state, and how you handle calls and cast, and nothing to do to tear it down. And then here's how you use it. You start the server with this spec, and then you can tell it increment, reset, increment, increment, and then you can say get. And hopefully this would show 2, I guess, and you can stop the server. So these are some simple examples of things you can do with these generic server stuff, which, if I understand right, this is how a lot of Erlang code is written, with generic server things. And it's built on top of these primitives that I showed you, that sort of expect and send. Yeah, I'm not going to talk much about it, but it has the same kind of things as Erlang. You can make supervisors, so you can have someone saying, okay, I'm going to monitor these processes. So let me just show how it can be used. So if we had our counter thing again, I can say, okay, I want to supervise one of these counter things, and if it dies, I'm going to restart it. So why might one of these, say we had the counter thing, why would it die? Well, micro Haskell, unlike GHC Haskell, if you overflow in arithmetic, you will get an exception, and if you don't handle that, you will die. So you could keep incrementing the counter until you hit max int, and then that would die. And then if you have it wrapped in this supervisor, it will just restart with a counter of 0. Is that what you want? I mean, you have to be careful when you restart, I guess. So this is sort of a sketch of all the threads that you have in a running Cloud Micro Haskell thing. So the processes are the thing that actually do the job, and then one thread per node that talks to the process threads that will do commands asking it to do things. And then you have a thread that does the communication to different nodes. So there can be lots more than just 2, and they will all look like this. And you will have a TCP connection to each of the other nodes. So the nice thing about this whole framework is that you never need to worry about how you set up the TCP connections and things like that. You have to say what the IP address and port numbers are for the other things you want to talk to, but then it will handle all those things automatically. Okay, so that was a bit about the cloud part of Cloud Micro Haskell. Then I just want to say a few words about the Micro Haskell part of it, which I'm more responsible for. So it's an implementation of Haskell that is Haskell 2010 plus a bunch of extensions, and it translates to combinators, and it has a pretty simple runtime that is written in C, and it uses very few things from libc. So you need to be able to allocate memory, and you need to be able to copy memory. So it needs like memcpy and these kind of functions. But you can turn off a lot of things. So you don't have to have printf, for instance, if your system you're running on don't have printf. So it's really made to be able to run on systems that have very limited abilities. So you can run it without any kind of operating system. So these boards here, they happen to run Zephyr OS because you need an Ethernet driver and TCP IP stack, which is difficult. So I guess Robert didn't want to write that himself. But he also has written stuff that runs on these boards, sort of on bare metal, where you can talk between you can have a trusted enclave of the processor that can run one copy of MicroHS, and then you can have a user one that runs a different copy. And there's also a student at Stanford who wrote an operating system in Micro Haskell with 4,000 lines or something and 1,300 lines of C code that runs on bare metal on a Raspberry Pi. So you can run things without any real support from an operating system. And you still get things like the kind of things, the processes, well, threads. You can do fork I/O as usual if you want to. Yes, so I said it translates to combinators, which means that there is no compiled code. Everything is in the heap. It's a bunch of combinators in the heap. So the heap is just application nodes that points to other nodes, and they might be primitive values like integers and floating point values and byte strings. And then there are primitive operations on these, like the combinators and the arithmetic and so on. So everything lives in the heap, which means that serialization is not that difficult. So there are primitives for serializing things. You can see the API there. So you give it an I/O handle and something to serialize. No constraints on what this might be. And it will send a byte stream over the handle. You can deserialize a handle and you get something back. And of course, it can't give you back anything of any type like the type signature seems to indicate. It will give you back whatever it is that byte stream encodes. So if you don't use this right, you will crash severely. So if you have sent an int and said, I expect a function, this will not work. So these are very unsafe primitives. But if you know that the sender and receiver agree on their types, then this is perfectly safe. But I'll show you a slide in a moment that makes it more safe if you want something more safe. And so the nice thing about having a primitive for serialization is that you can do things that are really hard to do if you try to do it from Haskell. I mean, impossible unless you have some cheating stuff. So it can preserve sharing. I mean, this will preserve sharing, and it will preserve cycles. And the serialized graphs are also portable, so you can serialize on one architecture with some particular CPU and then deserialize on another one with a different byte order or different word size. So there are a few things that cannot be serialized, and they might not come as any surprise. If you have a pointer into some piece of memory that you allocated with malloc for C, then yeah, of course, you can't. I mean, what would that be if you serialize that? And mvars and threads, that they also don't really make any sense. Serialization, well, you start on the graph, you do a depth-first search to find all the nodes that are reachable from that, and you keep track of which ones are shared, and then you do a second pass that actually produces the byte stream, and then first time you encounter a node, you will actually send that thing, and second time, if you get to the same node again, you will just emit the label saying, I've already sent you this thing. Serialization is not strict. It will send whatever it finds in memory. So if you have an unevaluated thunk, it will send that as is, which is nice if that's what you want. It can also be a foot gun because say that you have a compute server that, say, computes square root. And you said that the number, and it's supposed to compute the square root. And so it sends back to you skirt of this argument. So a function call to this argument. Well, if you just do it like that, it will just send back a thunk to you saying, OK, here it is. You compute the square root. I did my bit. I made the function an application node. So you have to make it strict at the sender if you want to actually pass that thing. So it can be tricky, but it's also very convenient. And deserialization is simple. You just have a parser and a table so you can recreate the sharing. If you want it to be more safe, there is this version that has a data constraint on the A. So you create a descriptor of the type. So it's not enough to send the name of the type or something like that, because the sender and receiver might not have the same name. So this sort of makes a description of the type and make sure that it's compatible with the receiver's description of the type. And there's very low overhead. If you send something with the same type over and over again, the way MicroHaskell sort of optimizes at runtime, it will only compute the descriptor once, so it will have this a 16-byte thing that it will prepend to the message, and at the other end it will just be a comparison of these. Okay, just so you know what the demo was. It's a 250 megahertz ARM processor. 640 byte? I thought it had 760. Oh, well. It doesn't have much, and it's running Zephyr OS, as I said. And also for talking to the network, Robert has written a package that is on Hackage called Network Lite, which is like network but light. It's possible to compile with MicroHS. Here is the code for the thing that toggles the LED. So there's on the top it calls a C function, C toggle, that toggles the LED, and it's using the generic server that I showed you earlier. So it's sort of a lot of code because you have to set up the generic server thing. And here is the thing that handles the button with some ... dots. So it has to fetch the server and talk to the registry and things like that. One can make several conclusions here. Cloud MicroHaskell enables Erlang-style programming across multiple nodes. Second, one can make the conclusion that I can't spell cloud. And it's fun. I think MicroHaskell is fun, and Cloud MicroHaskell is also fun. You can do things, and you can even run it on little boards like this. All right.
So one of the things that you can do in an Erlang system, which is quite nice, is you might have a number of nodes which together are providing a service, and then you want to upgrade the software. One of the things you can do then is maybe take down one node, upgrade the software on that, and you gradually work your way through the nodes until they're all upgraded, and the service never goes down. Now that's kind of problematic with the original Cloud Haskell approach when you have to have the same binary on all the nodes.
Yeah.
Do you think it would work with MicroHaskell? I can see that if you made changes like added constructors to a data type, that might lead to some confusion, but what do you say?
So right now, this descriptor, if you do the safe one, the descriptor requires the types to be exactly the same, but you could also loosen that so that it works if one is a subtype of the other. If they're not, I don't know how to do it. I mean, Erlang must have the same problem that if you the new system is not sort of properly a super system of the old one.
Erlang has a solution to it. Be careful.
I like that. I'll take that.
Can you show the type of expect again?
Probably can.
Or I guess the real question was, because I thought it was fairly polymorphic.
Yes.
Okay, right. So you have the serializable constraint.
Well, that's for Cloud Haskell.
Okay, right. So is expect just built on top of your serialization? Like if you expect the wrong thing, it'll crash, or do you do some clever type?
No. So if you use these, it would probably be good to use the safe one instead, and then they would have a data constraint. But data is a very mild constraint because everything can be in data.
Yeah, sure. So you said laziness could be a foot guy, right?
Yeah.
I assume you can, have a variant of send, perhaps called send NF or something that always evaluates the arguments to normal form before sending, or does that not work somehow?
Yes, but if you're sending a function, it's not quite clear what that means. Because a function can have unevaluated free variables, and that they can be hard to make sure that they are evaluated.
Okay. Another question is, if you send the same thing over and over again, is there some kind of like caching mechanism?
No. I mean, we can build that on top if you want to.
Okay, thanks.
Oh, I forgot to say, I should have said that Robert is on Discord and can answer any tricky questions.
Okay. Well, let's thank Leonard again. Do we have our next speaker?
Hello. I'm remote. Is that coming through?
It's coming through. All right, our next talk will be about a pedagogical subset of Haskell.
Hi, everyone. I'm Alex Hobbs. I'm a graduated master's student from the University of Warwick. Yeah, I'm very disappointed I can't be with you in person today, but I hope the conference is going well. I'd like to talk to you today about Tika, which is an interpreter and debugger for a pedagogical subset of Haskell. So a bit of introduction, some of which I'm sure you're aware. So the Glasgow Haskell compiler, or GHC, is the most popular compiler still for Haskell. As outlined on their webpage, it was designed for research in academia and is therefore primarily aimed at users who are adept in the language. So in the State of Haskell 2025 survey, 99.4% of regular Haskell users have reported using GHC. The next best was about 3.8%, so it really is by far the most used. In that same survey, they also surveyed people who had stopped using Haskell, and of those, around 14.7% had stopped after just one day, and a total of about 40% stopped within a month. And the barrier to entry issue has been discussed for many years in Haskell in that context. And while many educational tools exist across many formats, we feel that there's the need for one aimed specifically at learners who are just getting started with Haskell. In order to help onboarding of new Haskell learners, we've created Tika. This is an educational tool and stepping stone onto GHC and other comprehensive compilers. So there are four main features of Tika which I'd like to highlight for you. And the first is a modified subset of Haskell. This is suitable for new learners. It includes basic library functions so that new learners and students would get used to using these. The second is concise error messages, specifically ones that are adjustable to the experience level of the user. Programming language levels were discussed in a workshop a few years ago, and our testing showed that students benefited from switching between levels based on the task. And I'll get into more about that later. The third is targeted evaluation tracing. This has step-by-step explanation. And the fourth and final is an integrated IDE, along with an interactive read, evaluate, print loop, or REPL, which allows users to test individual components and functions. Not all people have access to strong teaching, so improving the accessibility for Haskell was a priority for us. And while all languages and tools are best learned under the direction of someone more experienced, Tika prioritizes simplicity and guidance. It allows students to be self-taught and individual and not have to rely so much on things like documentation and more generative AI as well. So Tika, supports reduced and slightly modified language to further its aims. So what does it include? Well, the main things you might expect in sort of a beginner level Haskell course, things like pure, referentially transparent functions, lazy evaluation, also Hindley-Milner type system with a parametric polymorphism, and a choice of static and dynamic type checking. The dynamic type checking is particularly useful for evaluation tracing, which I'll show in just a minute. We use a deliberately limited set of primitive value types. So doubles, characters, and booleans are the ones, primitives that we support. We found that supporting integers and floating points can be challenging. You have to use functions like from integral right from the get-go, which can feel somewhat meaningless to students without a knowledge of type classes. We also support, of course, tuples, lists, user-defined data types, pattern matching along with those, top-level pattern matching, case expressions, and if statements. And finally, unique to Tika, we support a special trace keyword, and evaluation tracing blocks, which allow us to limit what we trace, and so that students can highlight a specific part of their code, for example, for debugging purposes. The most notable things that Tika subset of Haskell does not include are guards, including at the top level. From observation and testing, we found that guards were the most inappropriately used language feature for beginners, and they often preferred repeated if statements approaches to something which would be more appropriate, like top-level pattern matching. The module keyword is not included. Instead, we use simplified import systems. Type classes are notably not included. These typically confuse newer students during testing when reading error messages, as we're about to see, so we decided to omit them for that purpose. And finally, user-controllable I/O and other monads. This is so that typically when learning Haskell, students have to complete exercises when first learning or be taught printing functions in order to have input and output to their programs. Instead, Tika's main function is non-monadic. It prints just the result instead. So here's an error message example, a common type of error message printed by GHCI. This is obviously a type error, but what questions might a beginner have in this? For example, what does interactive have to do with the error here? What is an instance? And maybe also, how can the number 1 be both a number and a character? And what is wrong with using the plus operator, the add addition operator, on the number 1, which is what this error message seems to suggest. So while the error in question here is trivial, this type error in a larger expression may not be. And although experienced GHC users may be used to seeing and understanding this type of error message, these are a specific pain point for new students to Haskell. And error messages refer to a system of inference, which is largely abstracted from use. For example, when using data types. Tika's approach to error message, to determine this, we sort of observed students over a period, over a new class, first-year university students, and also looking at GHC's error messages as we have. And we created the following set of principles to guide Tika's own. So error messages should be clear and concise, and always mention the proximate cause of the error and not just its effect. So here's one example. This is an error from exactly the same, an error message from the same error as we saw on the last slide. And here we say addition operator was used on A, which is of type char. It's not a double, it's not a number. They should also, where possible, refer to a line number and accurately point to its position. In the case of unexpected token, we list what tokens we would expect to find instead. This is one error which you may have come across, which you will, I'm sure you will come across in a GHC, where if you don't complete a statement due to layout rule violations, it will often throw the error to the next available line of code. And this is particularly confusing for newer students. So instead, Tika here says unexpected end of declaration, and it's expecting else. The prompt that it's waiting for an else block, which may not be so familiar to those who are used to imperative programming languages, where you might not need an else block in your if statements. And finally, the error message should offer different levels of explanation, depending on the user-chosen verbosity. And where helpful, we should suggest common reasons for the specific error. So this is the same error, but shown with different levels of verbosity. One just simply states that all values in a list should be of the same type, and the other suggests that maybe they should consider using a tuple. So syntactic errors can be caught and raised to the programmer, but semantic errors can often be hard to find, especially during the debugging process. Tracing steps through the lazy evaluation process and describing to the user what transformation is being made. So here's one example. Here is a very simple program. Again, it results in a type error. But using dynamic type checking, we don't raise this to the user immediately. Instead, we can step through one lazy evaluation step at a time, describing to the user what is happening each step. And so then, only once reaching the error state, does the error message make the most sense. This approach is Tika's default, and it sacrifices some type safety in return for teaching and learning opportunities. We also have the ability to use static type checking for those more comfortable, and the users were split during testing as to which they preferred. This was inspired by Prolog's trace mode and Haskellite's step-by-step justifications. This expands on both of them by including explanation, which is sort of like a personal tutor that can sit next to you. And it also really helps with the learning of certain core understanding, like key ideas, such as recursive functions, which will appear very early in many Haskell courses or textbooks. Different learners need different amounts of support. And so to cater to all, Tika offers levels. They control how much trace to show and how detailed that explanation should be. These are the 4 trace levels we offer. So no trace is self-explanatory. We have reduced case expressions, as case evaluation and pattern matching can often become very wordy, and the trace can become quite long. We have reduced operations only, which for most users, operations are simple to understand, and so may not need an explanation. But there's also the option for full evaluation tracing. And this can be really helpful it highlights the power of lazy evaluation and how a program is evaluated from start to finish. The verbosity levels, there are also 4 of those. We have no explanation, a concise, which uses more technical terminology, such as beta reduction, concise detail, which I'll come back to, and conversational. Conversational echoes Elm's style of error messaging, which feels very personable. It holds your hand. But many users during testing found that they wanted more explanation than the concise level, but didn't want the conversational style. So instead, we created this concise detail level, which sits in the middle, providing the same amount of detail, but with less explanation of it. So here's one simple program evaluated at both levels of 2. We see beta reduction. We skip the steps where the case is determined, the correct case is determined, and all of the addition, and we just get the answer to be 6. However, in larger code bases, we often find that these traces can become particularly long, even with reduced trace levels. So to counteract that, we introduce the trace keyword. And this block is a meta construct similar to Prolog SPY, helps limit the evaluation trace of larger programs. So here is one example. If we want to run the map function, but we only want to trace out function application. And the output looks as follows, where only the beta reduction and addition steps are shown in our trace map, the successor function on the list 1, 2, and 3. An output of this form clearly shows the behavior of the map function without needing to fully understand the function definition. And this has additional benefits if the learner has not yet been introduced to topics such as recursion, for example. And as I said before, it is useful for larger code bases and debugging and general understanding. The final roadblock that we found for new students of Haskell is the use of the command line, which for not everyone will be particularly familiar with this, and so it won't always be comfortable. Instead, we offer an IDE and a REPL, and the IDE looks like this. So this is a running of a simple program in Tika. Well, this is evaluating merge sort, again using a trace block. But if the user doesn't wants to test that a function, in this case merge, is working correctly, we give the console and REPL for that particular purpose. So they can type in, as you might expect from something like GHCI, merge, in this case 2.1, and this will give the output to that specific function. So it's interactive with the code that's being run. And having the code and the trace side by side really helps students to understand how the program is evaluating over time. So the evaluation of Tika itself was mostly done through user testing as well as a comparison with GHC. And that comparison can be seen more in the paper itself. The user test consisted of 23 first-year computer science students, and they were given a set of programming challenges and to compare their experience using Tika and GHC. And they'd only been learning for about 3 weeks or so, which we see as sort of the prime point and the most useful Tika can be. They were asked a series of 16 questions, some qualitative, some quantitative, and before and after the series of exercises to gauge their improvement and their preference of GHC or Tika. And the quantitative questions, we asked about their comfort level to gauge the benefit over time. The results can be seen here, the key results at least. On the left, we have a series of comfort questions for these basic topics. So function definitions, recursive functions, and tuples and lists. And on the right was a more general question asking students to rank on a scale of 1 to 10 how understandable and how actionable GHC's and Tika's error messages are. So the key takeaways was that for learners with under a month of Haskell experience, Tika's error messages were reported to be significantly more understandable and actionable than the more detailed and verbose messages of GHC, which are targeted, as I said before, at more experienced users. And on average, participants felt more comfortable with key beginner topics, such as recursive functions, lists, and tuples. So in conclusion, lowering the effort required to pick up Haskell is critical if we're to see the usage of the language increase, in a time where many popular programming languages now include functional features as well. Tika isn't meant to be competing with pre-existing compilers, but rather a helpful companion onto other materials and courses, even at the university level. We believe that once a user has outgrown Tika, they'll be comfortable picking up and beginning to understand fully fledged compilers, such as GHC. And so Tika is meant to act as a stepping stone onto other well-equipped compilers and interpreters. Tika is not just designed for one-liner trivial programs, but provides support for larger code bases and wider applications. Tika Standard Library, for example, supports about 51% of infix operators and about 36% of other functions included in Haskell's prelude. So it's a good starting point for students. We would like to continue work on Tika, expanding and improving its feature set, carrying out further studies into its benefits, and also in order to improve functional programming education more generally. So Tika is available following link, or by following this QR code. As I said, the tool remains in development. We want to continue working on it. And so contributions and feedback are warmly welcomed if you use this tool or have comments on it. Please feel free to email me with any thoughts, questions, and queries. as well. And if you use Tika in the classroom or other educational settings and want to share your experience or outcomes, please do reach out and I'd be really happy to discuss them. So thank you very much for listening to me today, and I'd be happy to take any questions.
All right, thank you so much for the great talk. Tika sounds really cool, and the trace feature in particular looks cool. I would be interested in trying it out in my teaching, and I looked at the README, and it looks like it runs on Windows and Linux, and it's not clear if it runs on macOS, and I was wondering if you have plans for macOS support.
Yeah, thank you. We do have, well, hopefully we'll have support for macOS. On the README as well, there is a list of instructions for building on different platforms, because we know not everyone has access to different platforms that it might be built for. So if you're able to build it yourself, because it hasn't been tested there, so it's difficult to say yet whether there might be other challenges with that. If you're able to build yourself, then that's perfect. But if not, then I'd be really happy if you reached out to me and we can try and sort that as well.
Thank you.
Okay, this might be a bit of a perverse question, but with regard to the people not liking the conversational mode, I hate to ask this, but everyone's asking about AI. If you were to throw an AI that were to smooth out the conversational mode, do you have any thoughts on whether, or did you try anything like that?
No, we haven't tried something like that yet. It definitely could be possible. Specifically, I think having a more concise explanation, but then at the end of a trace, you could use generative AI to sort of round out or condense that trace into some small steps, which might explain, and then the user might be able to ask questions to further sort of prompt the AI about what's happened in the evaluation of their program. That could be particularly useful, especially because, as we know, generative AI has been known to make mistakes. And so it being able to see that trace and then act upon that information would also be more accurate information.
It could also
so it definitely could be possible.
It could also maybe suggest next steps for the user to do if they're doing debugging, for example.
Yeah, absolutely. So it's not something we've tested yet, but it definitely could be a next step, yeah.
Thank you for great talk. I also, related to the past questions, really interested in that the trace. The time is like is I see is it possible to dump of the intermediate state of the trace? I mean that is I would like to kind of resume what kind of time machine wants is stop and trace and back it again and trace again. Is it possible?
So we don't currently offer sort of step-throughs of the trace. I think that's what you're saying, so where you can go to a certain step and go backwards and forwards between them. So we don't currently offer that, as it does run as an interpreter. It interprets the entire program, but I don't think it's beyond the realms of possibility.
Yes,
especially especially with using the REPL, where you're interacting with the program specifically. And I suppose that's maybe what you're getting at, is that you can also interact with the program, which I think is what the REPL is also meant to be for.
IT, thank you.
All right, well, fantastic. Let's thank Alex again. We'll wrap this session up with 2 lightning talks. Our first lightning talk will be by Laute, who will talk about modern Haskell profiling with Haskell Inspector.
Thank you. Wait. Yes, thank you for having it on the screen. Yes, today I'm allowed to, thanks for saying my name correctly. Today I will be talking about Haskell performance. If we're working on paper or small-scale Haskell, it's pretty easy to make Haskell really fast. But if we go to bigger and bigger systems with hundreds of dependencies, then occasionally when you upgrade something or you switch to a newer GHC, then you find out that performance is not the same as it was before, and then it can be quite a daunting task to find out what's really the problem. So one way to fix it is making Haskell better or GHC better, or make it always optimized perfectly, or warn about missing strictness annotations. But I don't know how to do this. So unfortunately today we'll have to talk about the second best thing. We have to accept that sometimes we have regressions, we have some problems, and but at least if we have them, we want to make it easier to fix. And the things that I'd like to look into are problems that occur in production binaries, like a service that runs for a long time, and after a while you find out that it slows down. I don't want to have a micro benchmark or something. Those are easy to fix already, and you can iterate on them. But I want to have the things where it's currently quite hard. So I want production-ready things, large programs that use tens of gigabytes of heap or maybe more. And I want to be able to run them live, since I want to be able to see what's going wrong in my actual service. And if every time I need to recompile, I need to restart, maybe need to decide which places I want to have more cost centers for, then that's really going to slow me down. So I think we can do better than what we currently have. And the way I think we can do that is called, well, Haskell Inspector. And Haskell Inspector contains three parts. One part is linked into the Haskell program. It's called the connector. It's written in C mostly. And if you're familiar with GHC debug, it's quite similar to that. It's a library that's linked into Haskell programs, and it provides a few debugging functionalities. In case of Haskell Inspector, it's capturing events from the runtime system. It's starting and stopping tasks. Breakpoints, some profilers. We'll come back to some details in the demo later. So that's the thing that is part of the program itself. This connects through a socket with to the Haskell Inspector server. And that server collects all the data. It's a headless program that can run typically close to the inspected Haskell program, since there's lots of data going back and forth. And then the third component is the user interface. We don't have to use it. There's a CLI that's part of the Haskell Inspector process itself. So we can, for batch processing or in a CI, or if we want to ask Claude to ask Haskell Inspector to investigate something, that also works that way. But for our more interactive investigations, we have a web UI. And that web UI is made to efficiently load the data. It does incremental data loading for time series data and everything else. It has some visualization, so you can interactively step through data, find out what's going wrong, and yeah, it has some interesting ways to display things. And the idea is that this whole system works while the program is running. The Haskell or the connector library sits dormant when nothing is happening. It's just part of your process. But once the Haskell Inspector connects, it starts to be able to do things. And so in the inspected process, it can do a few things. The Haskell Inspector can get live telemetry data. You can see what's going on. There's tracing using breakpoint and tracing engine, and profiling. There are a few more profiling options than you can get with the existing GHC things. And all these things you can start and stop without restarting your process. And if the program is running, you get live data. If the process is paused, you get a paused state of the program. The program does not run anymore, but you can do a much more detailed inspection. You can search the heap. And well, we already have some tools for searching the heap. And if anyone is familiar with GHC debug, it might be familiar. But I found that it was quite limiting. When I need to see some cause of some memory leak beforehand, I don't really know what kind of questions I want to ask. And for the type of things that I want to investigate, often there's loads of data. And if I use GHC heap and GHC debug to write a Haskell program to see what's going on, then it's pretty hard to find something that's performant enough to work actually in large scale. So I came up with something, a different language, small DSL for exploring the heap. It's called Haskell. And it has a list comprehension syntax. It's a nested relational DSL. So it's a sort of, it treats the heap like a database. The heap is a directed graph, so there's also path queries, so you can find all kinds of things. So you can, for example, ask which part of my heap is only reachable through tongues. So I have a few generators that source some data. I can join them and subtract one of them from the other. And I have an engine written in C. It's part of your, it's part of the connector. So if you use this whole Haskell inspector system, then this will eventually run a compiled version of the query, and it runs usually pretty fast. Like in many practical situations, I was able to get this thing to answer things 10 to 100 times faster than the things I was able to write with GHC heap. So how does it work? It takes the Haskell query, it compiles it to a core language, which is a pretty simple desugar thing with everything inlined as much as possible. Then it does makes a query plan, and not everything is completely supported, but most things, questions that I've been trying to ask about the heap will work. This plan is sent to the connector, then that searches the heap for you, it returns the results. And one of the interesting parts is that results can also return new queries. So if I have something where I return a few matched nodes, then I can run new queries on those nodes to find more information about those. And that's all exposed in the user interface as interactive exploration. There will be a release soon. This is where it's going to be on haskellinspector.lauter.com and my GitHub. But first, let's see what the system looks like in action. So to make use of Haskell Inspector, I have to depend on the Haskell Inspector connector library. I just made that a dependency in my program. To make the most use of it, I have to make sure that there are some info table maps, some GHC options for more debugging information. With all these options, nothing is really required that makes my program slower. Here I actually have profiling enabled, and that still works. But this will also give usable information for production-ready programs that run at production speed. So now I compiled this program, and I started it with my scripts, and I have installed the VS Code extension that's part of the Haskell inspector, and it found that there's one Haskell inspected program reachable in my current working directory. So it has a badge here, it pops up, so I can look for it. So retainer demo is active, I can connect to it, and now the Haskell inspector has connected. It's opened it in a separate pane. Let's move it here. So this is just a web pane that's handled by VS Code, and the first view is just a thread activity view. I have a few threads. This thread is doing something. If I want more details, then you can see that it's partly active, partly blocked on MVARs. You can see there's a short pause, 19 milliseconds. Maybe it was blocked in the GC for somehow. But these are things that are pretty hard to find with other tools. The whole, I can also see stack depth. So one thread is using more stack. I can see how much every thread is allocating. So at the start it was allocating here, but then later it's not allocating so much anymore. So that's the first view. This is just for a live program. I can also see how much heap it's using, how much time it's spent in GC, allocation rate. Just most of these things come from the event log. I can also inspect the event log directly. So if I have, how many? 1 minute. Okay. Let's see. My program is now running, but maybe I want to inspect or want to pause it at some point. I can trace. Now I have lots of trace points installed. These all the things that are annotated with IP data, they can also be traced and used as breakpoints. This thing, tree insert, is apparently a function that's being hit a lot. I can make that a breakpoint instead. Now my program is paused, and now I have a paused program, so I can search the heap. And here I can run this query. Now it downloads the heap. I can see in the log what it did. And here's my result. So I have TSOs that use a certain amount of memory. here I have main, I have thunks, I can find where these things come from, and if I have a thunk, then I can see where it was allocated. They're all backlinks to source code, and for each thunk or for each data in memory, I can also go to the memory detail view, where I can actually see how it's laid out in actual heap memory. That's pretty much the whole system. I'm still building it out, and I've used this to find actually quite a few actual memory leaks. And the source code should be up in a couple of weeks. I hope everyone will use it, and this will become a useful tool in the standard Haskell toolbox. Thanks for the attention.
Thank you for the talk. I've been looking for some Haskell profiler for a year now, and suddenly you give a talk about that. So that's great. And so I have some question about I have some small programs with some specific need I want to be able to profile, like how much time is spent on making tuples or getting out of tuples or allocating for closures, etc. This sort of thing. Do you think your tool will be able to help with that?
There is loads of profiling, also low-level profiling. I skipped over that in the talk. It's easiest to run this in long-running programs, since we can, let me see, but yeah, in principle, it should be possible. So everything you can already do with GHC profiling, like the dash prof and cost center profiling, it's also available in Haskell Inspector, and it's live. So if you connect to the program and record a profile, then you don't have to wait for like this. So normally, if you do a cost center profile with GHC, you run it, and you have to wait until it's done. And with Haskell Inspector, you can see it build up live. There's also a lower level profiling mode that does not require the profiling runtime, but uses the operational SDG stack. For micro optimizations, maybe if the profiling runtime skews the results too much, that's actually something where you can get better results from Haskell Inspector than from existing tools. Okay. But I've not really used it for short-term batch profiling very much yet.
All right, thank you.
This looks great. In fact, in particular, I want it. And I work in OCaml though, so dare I hope that we could swap in another collector for OCaml and in particular do these Haskell queries. I want those. Is that something that would in the future?
In principle, the language is not directly coupled to the GHC heap. So yeah, I've already made some abstraction layers since we need to be able to maintain this when GHC has future upgrades. There's already 2 different representations since the profiling heap has loads of words where in between. So objects look a little different. So maybe it's possible if there's a way to convert this. At the start of a Haskell query, basically it takes the whole heap and converts it to a CSR node index and does some hashing so you can do content matching by find duplicate things, that kind of thing. So most of the actual queries run on their own data structures, and only when you want to inspect individual closures again, you have to return back to the original heap. So it's fairly independent of it. I hope it's portable.
That's very exciting. Thank you.
All right. Fantastic. Let's thank Wouter again.
Thanks so much.
And in our second lightning talk of the session, Jan Willem will tell us about classes that count. I thought all classes counted.
Some count more than others. Okay, good. We're already in the correct mode. Yes, so thank you. I wanted to give a short little talk today on prefix matching using classes that count. I'm Jan Willem Maassen, and I work for Nectree. And at Nectree, we're building a little domain-specific language that lets you build agents and apps.
And as part of that, we're trying to deal with the information flow problem, because a lot of what we're worried about is the fact that more and more agents are going out and looking at our data, and we'd like to be able to govern which of our data agents are allowed to look at. And that means we need to build our own little flow control type system. And we're actually in the process of sort of prototyping different possible designs of that type system and experimenting with them. Now, most information flow policies tend to look like graph reachability of some sort, and there'll be these reaches constraints, and the only thing that'll matter is those things that have underscores there, which sort of talk about what kinds of edges are in our graph, and maybe some other things that talk about what kinds of nodes are in our graph. And data log turns out to be a great way to talk about those. So that was a data log, set of data log queries. If we ask Claude to build us a little data log engine, this is what it does for us. It'll just take all of our facts and turn them into a nice little Haskell algebraic data type. And then a rule becomes a function from a list of facts to a list of facts. And then we can write our rules down very naively as list comprehensions in Haskell. And the only sort of ugly thing here is this equality check, because we don't have the sort of implicit pattern matching plus equality semantics in Haskell that we do in Datalog. But that's not very hard. We know how to do that, right? So nice little realization of Datalog as list comprehensions and functions in Haskell. And the Datalog engine, such as it is this very naive one. It says, make a data.set out of all of the initial facts you start with, and then just run the rules on the set of facts, and that'll get us a new set of facts, and you mush those together into the database, add them to the database, and keep running until the database hits a fixed point. You don't discover any new facts. Right, and I want to thank my colleague Moritz Drexel, who really sort of did all the work up to this point. So we saw this, and this was like an agentic workflow where he was working through this with the Datalog engine on a more sophisticated rule set than the one I'm showing here. And we can imagine doing the same thing. We can elaborate this a bit, and in this case, I've instead elaborated it to a rule set involving Greek gods and goddesses. And we can talk about the families of the Greek gods and who's married to whom and who's parent. And we can ask things like, who are Zeus's children, and who's related to Zeus, either his parent, his child, or one of his more distant relatives. Okay, so that's great. We've built a tiny little Datalog engine. There's one small problem, right, which is this long pause here that happens when I tell it to compute the facts in the system, run the Datalog code for me. And the only reason there's that long pause is we didn't actually build an efficient Datalog engine, right? It was very, very inefficient. What I want to work through in the rest of this short talk is how to make that better. So we know there's this technique called semi-naive evaluation for Datalog. And the basic idea is we keep track of two sets of facts, right? We have the new facts, which we just added on the previous iteration, and then we have the old facts, which are facts that we added on earlier iterations of our fixed point algorithm. And then we want to run each rule, but we want to run each rule on at least one new fact every time we perform a rule evaluation. Then we'll take the results, that'll be our next set of new rules, new prime, and we'll continue iterating from there. All right, so that's semi-naive evaluation. The only problem is, how do we turn our nice Datalog rules here into something that's amenable to semi-naive evaluation? Well, trick number one is we add an extra argument every time we access the database again in our right-hand side. So now we have two rules that use the database twice, and so we need to give those two arguments each. And now I need to turn these all into a rule, each one into a rule, such that all the types match, and that we have something that we can run. So what's this rule function? Right? Well, we saw the right-hand sides are not uniformly typed, so this is probably going to need to be a type class. And in fact, what I'm going to do is I'm going to pass in not just the old database and the new database, but also the number of times that I have accessed the new database. And so initially we'll pass in 0 if we looked a couple of slides earlier. And I'm going to write this little class that counts, basically when we have a rule, we're going to pass in both the new database and the old database, but we're going to do so separately. And every time we pass in the new database, we're going to increment the number of times we've passed in the new database. And then when we're all done passing arguments in, if we never passed in the new database, we're just going to throw that result away and return set.empty. Otherwise, we're going to return the facts that our rule computed. All right, so that turns out to work pretty well. But there's another thing we can do using the same idea of writing classes over functions and sort of counting up missing arguments or counting up arguments, right? And that's this idea of fast prefix matching. So I have my semi-naive rules, and they're accessing the database, and I have all these equality checks. But what I'm doing is I'm iterating over the entire database, including irrelevant facts here. So I'd like to narrow it to just the facts that are relevant to me, and I'd like to do this using a little bit of prefix matching. So I have this @ combinator that lets me pass in a partially applied fact and match that in the database. And that works nicely because the database is ordered, and so we can sort of slice out chunks of the database, and we'll see that in the next slide or two. So I'm going to define this notion of a prefix. And the prefix is really just going to pair a now fully applied constructor with the number of arguments that we're missing from it. And how are we going to do that? Well, when we discover that there are still missing arguments, we'll increment the number of missing arguments and just pass undefined in for the argument that was omitted. And that works well until we have strict fields, and if we wanted to accommodate strict fields, we could do some clever thing like specifying a default value that we're going to plug in instead. Then we want to take that prefix, that pair of a partially applied constructor and a number of missing arguments, and we want to convert it to a function that we can use to slice out an ordered piece of the database, right? And it turns out we have this nice full-featured set library that actually provides drop while antitone and take while antitone, these two very nice functions that let us efficiently, in log time, pull out chunks of the database, split the database into pieces. And those didn't used to be in the set library years ago, and I think I was among the people who whined about their absence, though I think others whined far louder than I did and actually fixed it. And so we're going to write this toRange function that takes our prefix and turns it into an ordering. And so if we match the prefix, we're going to return equal, and if we're less than the prefix, we'll return less than, and if we were greater than, we'll return greater than. So how do we write this toRange function? Turns out it's not that hard. Now, this is a wall of text, but the thing I want you to understand about this wall of text is this is what we would get from an ORD instance if we asked the compiler to derive ORD, except that all the yellow stuff is stuff I've added into that ORD instance to handle the missing arguments, right? And all they do is they say, don't compare the arguments that we didn't pass in, right? So this is really just ORD with a little bit of fiddliness on the side. And we could write a generic instance for this. I wasn't that eager to do so yet because I'm still experimenting with this system. And how well does it work? Well, it turns out between these two very small optimizations, we've made the system about 200 times faster. So now it's actually interactive to use rather than running glacially every time I try and tweak my rules. And there are a couple of other little tweaks you can imagine doing, like sticking the database in a record rather than having a monolithic database of all the tuples. Those are a small gain, but nothing matches the gains that we've seen from the two optimizations that I described here. Just building little classes that know how to count missing arguments and making use of those to enable using a better algorithm under the covers. So with that, thank you very much. Oh yes, this is all on GitHub if you're curious.
I had a question. You sort of answered it, but how different is your, custom org class from just, what we would get with some sort of generic? How difficult do you think it would be to actually build the generic deriving mechanism?
I think the generic deriving mechanism would actually be really very easy. You can see here I've expressed this as a fold over compare instances. You probably couldn't exactly do that in a generic, but it would be relatively simple to do things like, decrement the expected arity as you sort of traversed along a set of fields. And so I expect this would actually be quite easy to realize generically.
With regard to your motivating problem in terms of allowed information flows, is it simple reachability, or are you imposing some sort of a lattice over what types of information is allowed to flow through?
So this is actually interesting because the example I showed you here doesn't impose a lattice structure beyond the usual set lattice, which is what we get out of naive data log. We are actually very interested in evaluation modulo lattice, and I think we can actually adapt this technique once we do this sort of recordization, which I didn't talk about here, of the database, so that the databases can, in fact, instead of being a set, be a map to a lattice element, and then things sort of generalize pretty straightforwardly from there.
I would very much be interested in talking to you about this.
Yes, I'd love to talk to you offline. Thank you very much.
And I believe we now have the final coffee break of the day before one more session of
All right, welcome to our last session of the afternoon. This session will feature one invited talk and then several lightning talks in quick succession. And so for our invited talk, I'm excited to welcome Josh Miller. I learned of Josh's work about a month and a half ago from a post on the Haskell.org blog about Haskell in production at HEB. If you don't know what HEB is, you're obviously not from Texas, because HEB is the biggest and best regional grocery store chain in Texas and much beloved by its fans. And if you didn't know, now you know that they run Haskell. So Josh is here to tell us about his work on Arbiter, his distributed job queue system that is being used in production at HEB and is also an open source project. And he's going to be telling us all All right, it is now time for lightning talks. And first up, we have Michael Adams, who's going to tell us about a fixed point generator for Haskell.
Testing, testing. All right. Hello. I'm very excited today to... Good? Okay. Hello. I'm very excited to share with you today the first public release of the language that my team has been working on for a couple of years. That is Fixin, the fixed point algorithm generator for Haskell. And really what this is a much more easy to program alternative to having to write work list algorithms, which I've had to write way too many of in my life. If you go to our website, we've got a ton of different examples and tutorials that I'm just giving you a taste of here today. And the reason I'm presenting this here, I chose to announce it at Haskell Symposium, is because Fixin is not intended to be a language in which you write your entire program. Rather, it's a language in which you write specific algorithms that we generate modules for that you link into your Haskell program. So what are examples of fixed point-oriented programming problems? Well, there's a lot of them. It varies from static analysis, automata minimization, dynamic programming, type checking, all sorts of different ones. They show up all over the place. And of course, nowadays, everyone has to mention AI. It turns out that this language is so good at quickly developing new static analyses that if you're using your AI to generate some coding, there's some unique property you want to check, rather than having to wait for someone to add that to an off-the-shelf analyzer, you can probably code this up in Fixin in an afternoon and have it verify that particular property of your generated code. Well, how do you program with these sorts of problems? Well, I'm going to answer that with a question. When we program over arrays, okay, we're Haskellers, we don't do that, but when we program over arrays, we use loops. When we program over trees, we use recursion. What do we use when we program over graphs? And by graphs, I don't just mean graph data structures. I mean anything that exhibits a graph structure in its computation. So in a static analysis, I might have multiple results that interdepend on each other, or in dynamic programming, even if there aren't cycles, the dependency structure isn't a standard tree that I can recur over. Well, to answer that, let's take a look at a very classic example, which is graph distance. So this is Dijkstra's algorithm. Isn't it beautiful? Okay, not really. It's about 20 lines of Haskell code, only 2 of which actually matter. One to say that edges add, the other one to say which edge to compute first, the shortest one first. All the rest of that is boilerplate that I should not have to write. Writing code like this is tedious, verbose, and fragile. Dijkstra is perhaps the simplest example of this. If you go to anything even slightly more complicated like tree automata minimization, which is, by the way, the one that really pushed me to realize the need for a language like this, or, God forbid, static analysis, it gets even worse. So our alternative to this is, instead of looking at it as a work list algorithm, we're going to consider it as a fixed point of inference rules. So to program this, we're first going to declare what are the facts that we're taking as input, in this case, the input graph. So we're going to declare that there is a relation that says, for example, that there is an edge from A to B of distance 1. And then we're also going to declare a set of facts that we're going to compute. So we say the distance from the start node to node A is bounded by 10. Then based on those, we set up the rules for how we do those computations. So the inference rule that we have says that if the distance to node A is bounded by D1, and there is an edge from A to B that is bounded by D2, then we know that the distance to B is bounded by D1 plus D2. Now note, I did not say the distance is D1 to D2. It's bounded by, because there might be another path. And so in order to represent this, the relations that we previously defined have to be over a lattice, so that if we ever discover that the distance is 1.3, and then later discover 1.7, we say, no, we're taking the join. The 1.3 is the current value that we keep computing with. And with that, we're done. This is enough code to generate all of that code we had before. Almost. This would solve graph distance, but it doesn't quite do Dijkstra, because Dijkstra has one more property, which is that when you can apply 2 copies of this rule, which one do we apply first? Well, what we do is we do another inference rule, and it's an inference rule that makes a declaration over the lattice ordering between applications of other inference rules. So we say we always choose the one with the shortest distance. Note that adding this does not have any semantic effect. It doesn't change what we're computing, it just results in us computing faster, which is an interesting property because you can write the design of your language and then later add these scheduling properties in order to speed it up while being guaranteed that you're not going to introduce any new bugs. So with Fixin, we've gone from something like this to something like this. We'll generate the code, generate a Haskell module you can link in and do your problems. Now, Dijkstra is just a simple example. We've also done more complicated examples in terms of, for example, static analysis. So in interval analysis, you just have to go through every form in the language you're analyzing and specify what the output data is in terms of the input data. It handles the dependency tracking and all of the updates. It's so much easier that when I had one of my students, we needed to benchmark performance relative to handwritten code. When he was done, he was like, no, I never want to write it by hand again. Fixin is just that much easier to work with. Also, because we are expressing these work list algorithms now as these fixed points over inference rules, they're at a higher level and more modular and compositional. You can write, for example, 2 different analyses, say an interval analysis and a parity analysis, and then after the fact, intermix them so that they are mutually refining and get better results than either one. So that's the general overview of Fixin. The main goal of this is a more ergonomic alternative to writing work queues that will integrate within your existing paradigm, in this case, Haskell. I've gone over quickly several of the features. We've got a few others I haven't mentioned here. And then there's a whole slew of optimizations that we've either already implemented or are in the process of implementing. So there's our website. There's our GitHub. Please give us a star so our grant agency will be happy with us. The status of this language is that it is pre-alpha. It is rapidly evolving. But even at this stage, we've got relatively good performance. There is an overhead. For example, Dijkstra, you're about 1.5 times slower. There are some static analysis where you're 10 times slower. However, number one, we're working to optimize that. But number two, more importantly, in exchange for that, you get a massive productivity increase in terms of the programmer. If you're interested, please get in contact with us. We would love to hear from you, especially applications or examples or use cases, so we can figure out what we can actually do with this language and demonstrate what it's useful for. And some of those might lead to interesting features or optimizations that we should add to the language. And if you want to help implement, so much the better. Finally, I will note that I do have funded PhD positions available if you are interested in working on this or working with my lab on other topics related to improving the ergonomics of programming languages. Thank you. Oh, and I have stickers if you're interested.
So I was going to ask about the performance of the Dijkstra algorithm, but you mentioned that. But can you also talk about why the performance is slower and in which parts of the Dijkstra algorithm or other algorithm that are slower than the handwritten one?
Okay, so the reason it is slower is because a lot of these fixed point algorithms, when you write them by hand, there are a lot of things that you implicitly inline or use specialized data structures for, as opposed to a general purpose queue. So we are starting from a baseline of just using a general purpose work queue and a general purpose fact database. And we have to index the maps and all that. But like with a Dijkstra, you might be represented as just an array that you're directly indexing into. So there are those sorts of things that we are working to optimize in abstract way so that at the high level, you can write it as if it were those higher level abstractions, but underneath it's actually optimizing those away.
Okay, thank you.
Okay.
By the way. All right, next up, we have Yao, who is going to tell us about the latest news in the world of freer arrows.
All right, hello everyone. My name is Yao, and today I'm going to talk about what's next with freer arrows. So what are freer arrows? Freer arrows are something we proposed and published a paper about in the Haskell Symposium last year. And since then, we have got some a little bit more progress, but probably not something complete. And this talk, you should consider this instead of like something that's complete. I'm going to show you this is more about like an invitation to collaboration or contribute to your ideas. Because I think free arrows are really cool, and we have the person who proposed arrows here today, John Hughes, and I really believe that the concept of arrows in general has a lot of potential. It has been used in many applications, but I think there should be more. And that is my goal, to look into this structure. So if you have any thoughts about free arrows, so I don't know what's going on. Uh-huh. Okay, thank you. Okay. Nothing. Oh. Just check. It was working in the previous talk. I don't see the screen.
Just replug. Yes. Yes. We see it.
Should it be mirror?
It's up there. Wait. Okay.
You have your speaker notes, right? Oh, I see. It's. So please think about this talk more of as an invitation to collaboration or for you to contribute about your ideas. If you have any thoughts about free arrows, I'm here, and you can also reach me by my email. And my PhD student Grant is also here. If Grant is waving here, yeah. All right, so yeah, please let us know. But also, like we have been collaborating with Lindsay and her student on choreographic programming with free arrows. So please talk to us. So what are free arrows? Well, maybe can the audience give me a hand if they are familiar with like free or freer monads? Okay, quite a few. Yeah, so we have freer monads that are very useful, right? So, but one thing with freer monads, even though it is very expressive, it lacks some capability, like especially static analysis. So the problem happens, so this is one representation of freer monads, right? And one problem with this definition is here. If you can see my cursor here, is here. There is a function that its input is x, and where this x come from is from some effectful computation ex, which means that if I want to do any analysis on this data structure, I have to carry a runtime that can give me either some simulation of runtime or something that can give me the result of this ex. So this can be a problem for if I want to static analysis, for example, if I want to just count the number of effects in my program, right? So in light of this, we propose a new data structure called freer arrows, So this is the definition of free arrows. It's a little bit complicated. You don't have to understand all this immediately, but essentially, it has two constructors. The first one is trying to kind of like defunctionalizing this ARR definition, this ARR operator of arrows, and comp is the composition between arrows. Okay, and here comp is composed of one function and some effect and another free arrow here. Okay, and there are some additional mechanism just to support the strength of what we call strength of arrows. Okay, so here's an example of using free arrows. Suppose I have some web service operations. I can just define some abstract data type that there's no semantics about the get or post here. This is purely syntactic. But I can mix in this syntactic representation using this inback function into my free arrow, and I can then choose to interpret this later, okay, by using this interp function. Recently, I've been thinking maybe I'm starting to think about renaming this as compile because there's the lack of runtime environment, which makes me feel like this is more closer to compiler, but also, I mean, compiler versus interpreter, this has always been a debate. We don't just have free arrows. We also have some variants of free arrows, such as the free pre-arrow. This is a simpler one that doesn't have the what people call strength in arrows. And there is also a freer choice arrow. That is essentially arrows are something with very sturdy control flow, and freer choice arrow adds something more to that. That is conditional. But that is a fixed amount of conditional. Okay, I cannot have arbitrary conditional. So this is 2 branches, but you can also go to 3 or several branches from that. So is this data structure actually useful? Yes, this is from our paper last year that is in collaboration with my student Grant, but also Lindsay and her student Gan. This is we actually apply free arrows to choreographic programming or the Haskell library. So what do we get from that? Well, first of all, we can get some sort of static endpoint projection. I've put quotation among the static here because different people have different opinions on static. The problem of this is a runtime endpoint projection. It doesn't happen during compile time, but it's still static because it doesn't require if any particular effect interpretation to do that. And the second thing we can do is what we call selective broadcasting. So one thing with choreographic programming is whenever you have conditionals, you need to be careful because you have to synchronize the choice among multiple different endpoints. And if you are using freer monas, this actually means that you don't want to use the full expressiveness of monas. You actually want a special constructor to be able to tell that you are doing conditional at some point. And we have to, whenever there's a conditional, we have to also broadcast our message to all the participants. But with the free arrows, essentially, we can do some static analysis and try to know which participants are in these conditionals and decide to just do a smaller subset of broadcast instead of the broadcast over the entire network. Sorry? Okay, so this is free arrows. For more detail, you can look into our paper from last year's Haskell Symposium. This paper here, or talk to me offline. But there's still, we feel like there's still a long way to go for free arrows because in particular, free arrows, are a few issues with free arrows. First of all, there's this ARR combinator that is still too dynamic, and sometimes that interfere with static analysis as well. And there's a syntax of free arrows, or arrows in general, that make it harder to use than ordinary monad. There's a do notation for arrows, but it's just a little bit more work than monad do notations. And third, the performance. In theory, when there's a static analysis, you should be able to have better performance, but our current experiments haven't supported that yet. And at last, we have one application, but there should be more applications, and I would love to talk to people about potential applications where using free arrows could be useful. I know that it has already been used in, well, arrows has generally been used in, for example, arrowized functional reactive programming, and in ICFP this year, I see it has also been used in property-based testing. I'm also looking for other potential applications. So I'm almost out of time. So one thing I'm going to mention is since then we also have some new work on that's further defunctionalize the arrows, which I currently call free abridged arrows. This is also got some ideas from latest papers on AFRP. And essentially, the problem is that we have ARR that is still too dynamic, so we are going to build some bridge that defunctionalize whenever you need to connect different effects. One benefit of this is we get actually also some cheaper interpreters compared with the original one here. I won't go into details. And we have also run some performance evaluations using some macro benchmarks. And so in the slides, you will see there are some something called A, that is free arrows, AF. That's a final encoding of free arrows. And we also have M and MF, which are more free monads, and a final encoding of free monads using some macro benchmark. But in general, we believe that we should be able to make arrows faster, but we haven't been able to figure out how. And we have not been good at profiling, especially like what GHC optimizations are there, etc. So I have been trying multiple different things. There are also a lot of variants I haven't shown you here today. But if you have some good ideas about how to profile or what kind of benchmark should be used and how the best practice for profiling, please let us know. And again, if you have any thoughts, please find us. All right.
All right, because we want to stay on time, so because of the technical Next up, we are going to learn about Turkish from Jumi.
Hello, everyone. I'm Jumi. Today I'm going to talk to you something about I've been working on in my free time, and that is a program language in Turkish where we bring the grammatical cases and moods of Turkish to the type system. So this is kind of a niche topic for this audience. I'm aware of that, but I'll do my best to make sure that all of you get something out of this. So a lot of PL folks have tried to make their program language look like a natural language. Famously, COBOL was one of these attempts. And there were attempts outside of the Anglosphere too, like this Russian-based program language that the Soviets had. It's less popular now, but people still do this. This trend hasn't completely ceased. So here's a replica of a Lisp dialect based on Levantine Arabic. And as late as last week, there was a standard ML dialect with Tamil keywords. So something that you probably haven't noticed here, unless you're a Russian, Arabic, or Tamil speaker, is that these program languages are linguistically not all that interesting. Their keywords are in these languages, but they don't use any other grammatical features from those languages. And I think that's a missed opportunity. There's especially one linguistic concept that I think would enrich the way that we program, and that is grammatical cases. If you don't speak a language in which cases are very prominent, let's have a quick look at the sentence. Give him a book. So here, why do we say him and not he? It is because this is one of the few places in modern English that we still have grammatical cases. Him here has the objective case. But there are languages out there where cases are more prominent, and today I'm going to focus on Turkish. Turkish has at least 7 cases. The declensions happen through suffixes. These suffixes take different forms according to vowel harmony. We're not going to spend our time learning this, of course, but if you have tried to learn, say, Latin, German, Russian, Hungarian, Finnish, this type of declension tables should look very familiar to you. So here's one way I think cases can enrich our programs. Suppose we want to write an expression that says difference of 5 and 3. So in Turkish, you would say, 5 ile 3'ün farkı. So notice how the word that corresponds to difference is at the end here. Noun phrases in Turkish have their head at the end. So here, the first part takes an instrumental case suffix. The second part takes a genitive case suffix. And the last part, the part that actually says difference, takes a possessive suffix. The thing is, the specific grammatical cases required in how you say difference allow you to switch the order in which you say the numbers in subtraction. So in either order, the listener will understand that this phrase means 2 and not -2. So we made a program language called KIP, in which that phrase is a function call, and the changing order of the arguments doesn't change the results as long as the cases of the arguments are unique. So this design choice comes with some other considerations. This is a Haskell symposium, so here's a quick OCaml refresher. OCaml has labeled arguments, which also allow flexible order of argument application. But what happens when the argument expressions have side effects? Well, obviously this can't happen in Haskell, but in OCaml it can. It turns out they're evaluated from right to left, just in general in OCaml, even though they're just technically unspecified. But let's put the flexible order of application in action. So I flip the order here. The result is still 2, but somehow the side effect is not happening in the order that I expect. It's still from, it's not happening from right to left. It's happening from right to left according to the order given in the original function definition. So I'm not really okay with that. Let's pretend that's okay for a second. Let's carry it. So we put parentheses around the first application and then pass the second argument separately. But that changed the order in which the side effects appeared. And I'm not really okay with that. I don't like this uncertainty. So let's make side effects explicit and isolated to avoid this, just like in Haskell, except without ever mentioning monads. So here's what an effective function looks like in KIP. The equivalent Haskell function looks like this. I don't have time to go over the morphological analysis of this entire function on the top, but there's some interesting stuff going on here. I'm going to explain that. We use infinitive verbs for names of effectful functions. That means you don't have to write the type in the type of that a function is effectful. KIP's morphological analyzer can figure out that this is an infinitive verb, and therefore it must be an effective function definition. We use sequential converbs. This is a grammatical construct in most Turkic languages to bind the result of an effective function to call a pure variable. But of course, in Haskell, you can only invoke an IO function from main. KIP's a bit more relaxed than that. You can have top-level effective function invocations, so otherwise like GHCI, so you can call it like this. But notice that the invocation of the effective function is an imperative mood. So when we're defining the effective function, we were saying to greet is to read the name and then print hello name. When we're calling the function, we're saying greet as a command. Okay, so now we have some understanding of what KIP programs look like. You might be asking, why is this technically interesting? Why does this language have a place in a PL venue? The main reason is how we deal with ambiguity. So like most other natural languages, Turkish morphology is ambiguous. A surface form can have different possible analyses, and a parser alone often cannot know which reading is intended. So KIP, using an external morphological analyzer, parses these identifiers with the candidate sets of possible roots and possible cases, and then the type system prunes these candidate sets using type-directed constraint solving. If there are no candidates left, then you have a good old-fashioned type error. If you have multiple candidates left, you have an ambiguity error. And then usually you almost always want a single correct candidate. So this is a kind of a novel approach for natural language-based programming languages, because the others usually treat such ambiguities as parse errors. So instead, we solve these ambiguities in type-directed elaboration, which allows us to accept more well-typed programs. KIP has an ML-like type system with predicative polymorphism and algebraic data types, but keep in mind that flexible application orders are everywhere in KIP, because we have parameters of data types, arguments of data type constructors, patterns on data type constructors. These all support flexible application order. And especially combined with the ambiguities that we just talked about, this gets kind of tricky to get right. A less consequential point that I find quite cool is that head final syntax is like reverse Polish notation. So remember this expression. This is how we say the difference of 5 and 3 in Turkish. The word for difference is the last word. This is also a valid KIP expression. So let's do a more complicated expression. If you were writing this expression in some other language, you usually have to put the sub-expressions in parentheses. But interestingly, you don't have to do that in KIP. Since the operation is at the end, this is like parsing reverse Polish notation, and famously that does not require parentheses, so you can just write it this way. And this both reads and looks like natural language and has no ambiguity. I do want to note here that what I'm doing here is not natural language programming in the Dijkstra sense. We're not writing natural language prose and expecting to compute. We're just borrowing ideas from linguistics to make our program languages richer. These ideas may make our languages less usable or more usable. We don't really know that. We haven't done user studies. We're just trying to conduct an experiment, a type theory experiment, if you will, to see if it's doable, and it was. I should talk a bit about implementation. It's in Haskell, has a REPL that runs the way you expect. We even compiled to WebAssembly through GHC, and it runs in the browser. So here we're running the program that we saw earlier. It's prompting us for a name. I type the name, it prints hello. That's what you would expect. We even have an LSP server implemented in Haskell. We have a VS Code plugin, a Vim plugin, all of that interacts with that LSP server. It has all the nice features that you would expect, like hovering, going through the definitions, and such. And we have all kinds of example programs listed in KIP, including even a DPLL-based SAT solver. And that's all I have for you today. So we made a Turkish programming language called KIP, in which all function arguments carry grammatical cases. Pure definitions are noun phrases. Effectful definitions are verb phrases in the infinitive. Effective function calls appear in the imperative mood. You can find the repo and the playground, the links here. We also have a short paper at Hatra. Thanks for listening.
Maybe you could take inspiration from Stephanie's talk yesterday about verse, and instead when you have two different parses, you could just have a stream of computation that produces a stream of values.
Yeah, but I wanted to make a mini Haskell, so.
How would you deal with searching for identifiers in your code if the identifiers
Sorry,
are inflected?
what for identifiers? I missed what you were
How would you search for identifiers in your code if your identifiers are inflected?
Do
you have any ideas on that?
Yeah, in the top level, the identifiers can be in two cases, either nominative or the possessive suffix. So that's easier to parse usually, and that's what we depend on.
So do I understand correctly that all names, including function argument names, are cased? So like I was wondering about sort of higher monadic code. Like I was wondering how you write something like sequence, right? Where it's like to sequence a list of actions is to act and then I don't know how to say that. So
okay, we can discuss it offline if you find me afterwards. Yeah.
One of the things I found interesting was that you have a different way of or you have a restriction on whether or not something is an effectful or non-effectful computation, and that comes out in the identifier itself. And I wanted to know if that's something that you extend further. I'm thinking like Hungarian notation, where part of the actual identifier in some sense tells you what the type is for things other than just effective.
Yeah, I mean, there's a suffix for the infinitive verb morphologically, and there's no suffix for the imperative call, but you can still infer that it's a verb usually. Yeah, I mean, if it's defined in infinitive, you know for sure that that one's a verb. So when you see it in the imperative, you can tell that it's a effective function call. Yeah.
And last up for today, and this is our last scheduled event of the day, JJ is going to tell us about their wiki tool implemented in Haskell.
All right. Hello. Yeah, so this is my lightning talk for the Haskell Symposium. It is sort of a little bit of a similar talk to the previous one, in which I have written a thing in Haskell, and I'm excited to tell you about it. So a little bit about me. I just graduated from my undergrad at UBC, where I did math and linguistics and a little bit of computer science, but really just PL. I'm employed for the summer as a linguist. I don't know what's going to happen after that, but linguistics has been a really strong inspiration on this tool because I've been looking around, and there are just some things which I have not been able to find, so that's been, yeah, it's been the inspiration there. So yeah, this tool is called Sticks. I kind of call it a tool for semantic thought as a blurb that doesn't very, as like a bit of a blurb. And more plain language, it's a wiki tool. It's a tool for kind of writing down notes and collecting notes and putting them together. But this blurb I've kind of broken down as the structure of this talk. I'm first going to talk about some of the inspirations behind this. The primary one is another tool that kind of bills itself as a tool for thought. It's this Forrester tool. Then I'm going to talk about the semantics part of this and what exactly I mean by semantics in note-taking. And then finally, I will be discussing some of this room's favorite language, Haskell. So first off, Forrester. Forrester is this wiki tool by John M. Sterling, who might be known to the functional programming community for different stuff, and Kento Okura. It lets you write your notes in this like LaTeX-like DSL and get an HTML or an XML wiki. With support, and by wiki, I really mean two things here. It has support for what is called transclusion, which is like embedding your notes. They call it transclusion. I'm not sure where this comes from. I'm kind of curious. And backlinking. And that's really like the core of this wiki. The transclusion means that you can build your notes up from little small note cards and compose them into one large page. And the backlinks mean that you can kind of navigate around the wiki going forward and backwards. That's kind of a little bit of the essence of hypertext. And I've put some example syntax up here. And this is great, but fundamentally, this is a tool for computer scientists and mathematicians. You can see it in the syntax. There's special support for embedded math, embedding LaTeX diagrams, and more generally, there's this really interesting notion of notational macros. And John Sterling has waxed some about this. I don't have time to get into it. But this isn't enough for some other fields, like linguistics. In linguistics, one structure that we really just so commonly have to deal with are interlinear glosses. And these are word and phrase aligned chunks of typesetting. And every field of linguistics has to deal with this. It's a really important primitive. And so the common tools in linguistics are LaTeX and Microsoft Word. That's not amazing. So what kind of inspired this is this other new tool called Typest. Typest is a programming language and also a corresponding typesetting system and markup language. It pretty directly competes with LaTeX, except it has kind of taken inspiration from the past 40 years of programming languages, which is really lovely. There's not a lot of venues that accept this as like a language in which you can write your papers, but here in something maybe JFP, we'll see. And really, I think this quote exemplifies pretty well how I feel about it. Markup is an interesting target to write a programming language for. In fact, I really agree with this quote. And anyway, so despite being a typesetting language, types also, and like, so you want to care about appearance more than anything. Types also has a really rich semantics. It's primarily used for accessibility support, but recently it has been used for developing their HTML export, their semantics-focused HTML export. So all of the non-placement blocks in the language, which include things like figures and images and mathematics, which compiles to MathML, which is now a evergreen web standard, which is very lovely, are compiled directly to HTML with sort of appropriate semantics given in this HTML format. And crucially, packages, because types has a notion of packages too, in a similar sort of fashion to LaTeX, can add their own HTML support as a backend and style that. So like this interlinear glosses package that I'm using here. This slideshow is also written in types. It's not actually targeting HTML, but I should be showing a quick example of that later, now. So to tie this kind of back to this workshop a little bit, I wrote a types wiki tool in Haskell. This is a little code block of the main compiler pipeline. So it's, I'm not going to go into much about that. But I am going to, I have a little, yes. So I have a little demo here. On the left here is the code behind like a page of this wiki. And on the right here is its rendering in HTML. And you can see if I scroll up here, there's some typesetting that this looks kind of similar to Markdown. It translates directly into the basic HTML elements. But then down here, there's also this more complicated typesetting. And over here on this left, I have this block, which is using an external package for typesetting interlinear glosses. And over here on the right, I have this compiling to HTML. Same for these diagrams, so like syntax trees, parse trees, and yeah, this is kind of cool. I like that this. I find this little list syntax for these proof trees pretty cute. But one really cool thing about this is that I didn't write these libraries. This is libraries from just the ecosystem. I just added a bit of like HTML support, but like that's going to be contributed upstream, and then anybody can just pull these down and use them. So let me go back to the slides. Yeah, so I think that this is a kind of interesting comparison with Forester. Forester is an academic tool. It was in development for 2 years. It's been 3 years now since its release. They released their 6.0 version, I think, yesterday, which is pretty cool. And it's like large, it's complicated. It's like 10,000 lines of OCaml. And by comparison, and not to toot my own horn, Forester is much more stable and much more performant. This sticks tool that I've been developing is kind of, I've only been working on it for like 3 months or so. It's like 600 lines of Haskell. It was developed a whole lot faster than Forester. So why is that? Well, there's something out there that's 10xing my productivity. Libraries. Haskell has amazing libraries. Haskell and Pandoc made it such that I didn't have to write almost any boilerplate. Like among those 600 lines, it's like 500 lines of implementing like the core wiki features and 100 lines for the CLI and such. And these libraries have really good abstractions, which I just think is a really lovely win for Haskell here. I don't even write Haskell very often normally. I'm a very big fan of lean. I like my front arrows and my back arrows, and so this is kind of what most of the code in that code base looks like. Not exactly maybe idiomatic Haskell, but it was just simply the best tool for the job. Thanks again to those really wonderful abstractions in the library. So that's about all I have for you all. If you all are interested in, this sort of wiki tool with, and I suppose support for like complicated typesetting in notes and HTML, yeah, give it a look. I've got a little bit of documentation up online. I've got the code up online. It's still very much a work in progress. There's a lot of open bugs, and there's some particularly bad performance issues that I have not had time to fix before ICFP has been very busy. But yeah, if you play around with this and think up any features you might like, feel free to accost me online or after the session. And as a last talk of the day, it's my pleasure to say That's all, folks.
All right, well, that is indeed all, folks. If you enjoyed the lightning talks and you think you might want to give a lightning talk tomorrow, we do still have time. So there is a form that's linked from the Haskell Symposium webpage that you can fill out to do a last-minute lightning talk tomorrow afternoon. Also, tomorrow afternoon, we have planned right now it's 90 minutes. I guess that could shrink if we get a lot of lightning talk submissions, but we have a 90-minute unconferencing session planned. And if you don't know what unconferencing is when you, the attendees, make the schedule. So tomorrow morning, I'm going to bring some Post-it notes, and we'll have a place where people can make suggestions of what they would like to talk about during the unconferencing session. And then it won't be presentations up on the stage like this, but rather semi-organized small group discussions about anything that's been discussed this week that you'd like to talk about more. So more about that tomorrow. But think about what you might want to spend your last 90 minutes at ICFP discussing, and that might be a good topic for unconferencing. Otherwise, with that, we're done for the day. So let's thank again all of our speakers from today. And thanks again to the awesome AV team for their work.